the cosmos has a way of keeping us humble. And October 2025 is about to deliver a masterclass in cosmic humility that will challenge everything we thought we knew about visitors from deep space. Two objects are currently racing toward our sun, arriving within weeks of each other in what should be a once-in-a-million-year coincidence. But here's the thing that's keeping astronomers awake at night. One of these visitors carries chemical fingerprints that break the fundamental rules of how matter should behave in space. What we're witnessing unfold above our heads right now represents either the most extraordinary cosmic coincidence in recorded history, or evidence that something far more deliberate is happening in the darkness between stars. By the time you finish watching this investigation, you'll understand why the world's most powerful telescopes are trained on these objects, with an intensity usually reserved for potential planet killers. The first visitor emerged from the constellation Serpentis in July 2025, designated 3I Atlas after the automated survey that caught it streaking through space at impossible velocities. This interstellar wanderer, the third confirmed visitor from beyond our solar system, carries the mathematical signature of an object that will never return. Its hyperbolic trajectory marks it as a true alien, born around another star, now making its one and only passage through our cosmic neighborhood. But 3I Atlas wasn't supposed to have company. Wasn't. The statistical odds of two significant objects arriving simultaneously should be vanishingly small. Yet in September, as astronomers were still puzzling over their interstellar guest, another visitor materialized from the solar glare like a ghost stepping into lamplight. Comet C/2025 R2, discovered in solar and heliospheric observatory data, announced itself with a brilliant tail that stretched across degrees of sky. Now here's where the mathematics of coincidence start breaking down. These two objects, born in completely different regions of space and following entirely different types of orbits, are timing their closest approaches to our sun within a narrow window that spans just weeks. 3I Atlas will reach its closest point to our star around October 29th, while SWAN R2, as astronomers have dubbed the brilliant newcomer, already swept past its own solar encounter in September and is now heading for its closest approach to Earth on October 21st. The precision of this timing would be remarkable enough on its own, but it's the chemistry that transforms remarkable into genuinely unsettling. When the world's most sensitive spectrographs turned toward 3I Atlas, they discovered something that makes veteran astronomers pause and recalculate their assumptions about how the universe works. The object is glowing with prominent nickel emissions, creating part of that distinctive green tint that's made it a favorite target for astrophotographers. But here's the problem. Nickel almost never appears alone in cosmic chemistry. It should be accompanied by iron in predictable ratios that reflect the nuclear processes that forged these elements in stellar cores billions of years ago. 3I Atlas seems to have missed that particular chemistry lesson. The very large telescope's observations show strong nickel emission lines standing out clearly against the complex spectrum, while the same sensitive instruments searched for iron and found essentially nothing. The upper limits are so stringent that if iron were present in normal cosmic abundances, it should have been easily detectable. It's as if someone or something selectively removed one element while leaving its companion untouched. This chemical peculiarity has spawned numerous attempts at explanation, each trying to reconcile the observations with known physics. Perhaps nickel-bearing organic compounds, stable in the extreme cold of interstellar space, break down under solar heating to preferentially release nickel atoms into the gas phase. Perhaps space weathering processes operating over millions of years have altered surface chemistry in ways we don't fully understand. The universe is under no obligation to conform to human expectations about elemental behavior. Yet SWAN R2 presents its own catalogue of mysteries that compound rather than resolve the puzzle. This massive visitor from our own solar system's outer reaches is producing one of the most spectacular comet displays visible from Earth in recent years. Its tail development and brightness evolution follow familiar patterns. reassuring astronomers that at least one of our October visitors behaves according to textbook expectations. But the timing of its emergence, virtually simultaneous with 3I Atlas's passage through our inner solar system, creates a juxtaposition that challenges the comfortable assumption that cosmic events follow random distributions. The observational campaign, coordinated around both objects, represents one of the most intensive studies ever conducted of simultaneous cosmic visitors. The Hubble Space Telescope provides high-resolution imagery tracking changes in coma structure and brightness over time. The James Webb Space Telescope contributes infrared capabilities that reveal details about chemical composition invisible to ground-based observations. The Very Large Telescope in Chile breaks each visitor's light into constituent colors, identifying specific molecules and atoms glowing in their respective atmospheres. But October brings a cruel twist to this observational feast. As both objects approach their most scientifically interesting phases, they will sink deeper into solar glare as viewed from Earth. The same solar heating that triggers the most dramatic outgassing and potential revelations also positions them at increasingly challenging viewing angles from our planet's perspective. Ground-based telescopes will eventually lose the ability to track them during the most critical phases of their solar encounters. This observational blackout period represents more than just an inconvenience. During the weeks when Earth-based telescopes cannot observe them, both objects will undergo their most intense solar heating. If anything unusual is going to happen, if any hidden characteristics are going to reveal themselves, it will likely occur during these invisible weeks when our instruments fall silent one by one. Mars serves as our forward observer during this crucial period. The Red Planet's suite of orbiting spacecraft, missions designed to study Martian weather and geology, will turn their instruments toward these passing visitors during their October encounters. The European Space Agency has announced preliminary plans to coordinate observations using the ExoMars Trace Gas Orbiter and other assets positioned around Mars. These observations will be opportunistic rather than planned, but they may provide our only clear view during the critical phases when Earth-based telescopes go blind. The viewing geometry from Mars offers advantages unavailable from any Earth-based location. The red planet will be positioned at different angles relative to the Sun-comet lines, potentially revealing aspects of coma and tail structure that remain hidden from our terrestrial perspective. The lack of atmospheric interference eliminates the seeing limitations and absorption effects that constrain ground-based observations, allowing for potentially sharper images and more accurate measurements. Yet even with multiple viewpoints and sophisticated instruments, fundamental questions persist that cut to the heart of what we're actually witnessing. The coincidence of timing continues to nag at researchers who have spent their careers studying the statistical mechanics of solar system dynamics. In a cosmos where chance encounters typically span millions of years, why are we observing two such dramatically different visitors arriving virtually simultaneously? The chemical signatures add another layer of complexity to this puzzle. While natural processes can potentially explain the unusual nickel emissions from 3I Atlas, the absence of accompanying iron creates a compositional fingerprint unlike anything in our catalogues of asteroids, comets, or meteorites. It's chemistry that makes sense if you imagine selective processing or refining, but challenges our understanding of how natural formation processes should work in the cold depths of interstellar space. SWAN R2's conventional behavior provides an important control in this cosmic experiment. Here we have a visitor that follows all the expected rules of comet physics, brightening predictably as it approaches the Sun, developing spectacular tail structures that align with radiation pressure and solar wind interactions, exactly as theory predicts. Its presence alongside the enigmatic 3I Atlas creates a natural comparison between normal and anomalous behavior in objects undergoing similar thermal processing. The international coordination required for this observational campaign illustrates how modern astronomy operates as a global enterprise. Telescopes in Chile track objects during Southern Hemisphere nights, then hand off coverage to facilities in Hawaii and the Canary Islands as Earth's rotation carries the visitors into different viewing zones. Space-based observatories provide continuity across day-night cycles and atmospheric conditions that might block ground-based observations. But perhaps the most intriguing aspect of this October convergence involves what we almost missed entirely. Both visitors spent months approaching our solar system before becoming bright enough for detection. How many similar objects might have passed through unnoticed, lacking the size, composition, or favorable geometry needed for our surveys to find them? The detection efficiency for cosmic visitors depends heavily on their characteristics and approach trajectories, suggesting we may be observing only the most visible representatives of a much larger population. Statistical models indicate that for every interstellar object we detect, dozens or hundreds might pass through unobserved. The objects we do find represent those fortunate enough to develop substantial atmospheres, approach from favorable directions, or achieve sufficient brightness for our instruments to distinguish them from background stars. This selection effect means our current sample of interstellar visitors may not represent the true diversity of what crosses through our cosmic neighborhood on regular schedules. As October 2025 progresses, both visitors continue their relentless approaches toward their respective encounters with our sun's intense radiation and gravitational influence. Each day brings new observations, refined orbital calculations, and additional pieces of a puzzle that grows more complex rather than simpler with accumulated data. The green-tinged glow of 3I Atlas has become a distinctive feature in autumn skies for those with telescopic equipment, while SWAN R2 dominates the western horizon after sunset for anyone with binoculars and clear viewing conditions. What emerges from months of intensive observation is a portrait of cosmic visitors that challenge our categories and expectations in subtle but persistent ways. The universe has delivered two objects to our doorstep that invite comparison while resisting easy classification. One follows rules we recognize, the other operates according to chemistry we're still trying to understand. The dance between these cosmic visitors becomes even more intricate when we examine the forces that govern their motion through space. While SWAN R2 follows the predictable choreography of gravitational mechanics, tracing an elongated ellipse that carries it from the frigid outer reaches beyond Neptune to within half an astronomical unit of our Sun, 3I Atlas moves to an entirely different rhythm. Its hyperbolic trajectory speaks of velocities so extreme that our Sun's gravitational embrace cannot capture this wanderer, marking it forever as a tourist rather than a resident. But here's where the physics starts painting an unsettling picture. The energy requirements to accelerate any substantial mass to interstellar velocities are staggering beyond comprehension. Natural ejection mechanisms, whether from planetary formation chaos or stellar encounters, typically produce objects with modest excess velocities. Yet, 3I Atlas carries kinetic energy, suggesting it was either flung from its birth system with extraordinary violence, or has been accelerating through mechanisms we don't fully understand during its millions of years crossing the galactic void. The rotation characteristics of both visitors add another dimension to this mystery. Most small bodies tumble chaotically through space, their spin states altered by countless impacts and gravitational encounters throughout their histories. Natural objects display erratic brightness variations as different faces catch and reflect sunlight during their tumbling motion. But 3I Atlas exhibits rotation patterns that appear almost controlled, with periodic variations that suggest stable spin axis orientation rather than the chaotic tumbling expected from a collision fragment. This rotational stability becomes even more remarkable when considered alongside the object's chemical composition. The selective presence of nickel without accompanying iron could theoretically result from industrial processes that separate and concentrate specific elements. If 3I Atlas was some form of manufactured construct, its controlled rotation would make perfect sense as evidence of attitude management systems designed to optimize solar energy collection or maintain communication alignment with distant receivers. The thermal behavior of both objects provides another window into their fundamental nature. SWAN R2 follows the textbook physics of ice sublimation, brightening predictably as solar heating vaporizes frozen gases and releases dust particles trapped within its nucleus. The relationship between distance from the sun and observed brightness matches computer models with reassuring precision, confirming our understanding of how pristine materials from the outer solar system respond to intense stellar radiation. 3I Atlas tells a more complex thermal story. Its brightness evolution shows patterns that don't quite match standard models of ice sublimation. The object appears to maintain activity levels that require either unusually volatile surface materials or internal heat sources beyond simple solar warming. Some researchers have proposed that radioactive decay within the nucleus could provide additional energy, but the required concentrations of unstable isotopes would exceed anything observed in natural samples. The spectroscopic fingerprints revealed by the world's most powerful instruments continue to deepen rather than resolve these mysteries. Beyond the prominent nickel emissions that first captured attention, 3I Atlas displays other chemical signatures that exist at the boundary between exotic and impossible. Cyanogen molecules contribute to its green coloration, but their abundance relative to other carbon-bearing species doesn't match patterns observed in comets from our own solar system. Carbon dioxide dominates the infrared spectrum captured by the James Webb Space Telescope, with water vapor playing a surprisingly minor role during the early phases of observed activity. This chemical hierarchy tells a story of formation in environments where temperatures and pressures differed significantly from conditions in our own stellar neighborhood. Different stars create different temperature profiles in their surrounding disks during planet formation, potentially leading to objects with compositions unlike anything familiar from our local cosmic environment. The European Space Agency's analysis of these infrared observations notes that the low water-to-carbon dioxide ratio represents typical early activation behavior where the most volatile ices sublimate first. As 3I Atlas continues toward its October encounter with our Sun, the relative contribution of water vapor should increase as less volatile ices reach their sublimation temperatures. This prediction provides a crucial test of whether we're observing natural physical processes or something more deliberately engineered. Production rates of different molecular species offer another diagnostic tool for distinguishing between natural and artificial origins. As both visitors approach closer to our Sun, they should release water vapor, carbon dioxide, and other gases at rates determined by well-understood physics of ice sublimation. Any significant deviations from these predicted curves might suggest internal processes beyond simple solar heating. The amateur astronomy community has played an unexpectedly crucial role in monitoring these production rate changes over time. High-quality imaging from experienced observers around the world provides temporal coverage that professional telescopes, with their limited observing time and competing research priorities, cannot match. These dedicated skywatchers have documented subtle variations in coma brightness and tail development that complement the detailed spectroscopic studies conducted by major observatories. Social media platforms have become repositories for real-time observational data, creating a global network of citizen scientists contributing to humanity's understanding of these cosmic visitors. The collaborative effort represents one of the largest coordinated scientific responses to astronomical phenomena in recent history, demonstrating how modern technology enables unprecedented levels of public participation in cutting-edge research. But this democratic approach to cosmic observation has also amplified certain interpretations that extend far beyond what the data actually supports. The unusual chemical signatures observed in 3I Atlas have inspired speculation about industrial processes, manufacturing signatures, or even deliberate construction that goes well beyond the cautious language typically used in peer-reviewed scientific publications. NASA's official communications maintain careful balance, acknowledging the genuinely unusual characteristics of 3I Atlas, while emphasizing that exotic doesn't necessarily mean artificial. Space agency scientists note that our sample of interstellar visitors remains extremely small, making it difficult to establish what should be considered normal for objects originating around other stars. Chemical compositions that seem impossible by solar system standards might be perfectly natural products of stellar environments with different masses, luminosities, or evolutionary histories. The distinction between extraordinary and merely exotic becomes crucial when evaluating claims about artificial origins. Extraordinary chemistry might suggest technological processes, while exotic chemistry could simply reflect formation conditions we've never encountered before. The challenge lies in developing observational tests that can reliably distinguish between these possibilities using instruments designed to study natural rather than potentially artificial phenomena. The upcoming solar encounters will provide the most definitive tests of competing hypotheses about both visitors. Natural objects undergoing thermal processing near the Sun should display predictable patterns of gas and dust release, brightness evolution, and spectral changes. Any significant deviations from these expectations might indicate processes beyond conventional ice sublimation and gravitational mechanics. The cruel irony is that these crucial tests will occur precisely when our observational capabilities become most limited. As both objects sink deeper into solar glare during their closest approaches, Earth-based telescopes will lose the ability to monitor the very phases that should reveal their true nature. The observational blackout period will span weeks, possibly months, during which the most scientifically valuable processes will unfold beyond the reach of our most sophisticated instruments. Mars-based observations during 3I Atlas's October flyby represent our best hope for maintaining surveillance during this critical phase. The red planet's orbital position provides viewing geometry unavailable from Earth, potentially revealing structural details and behavioral patterns invisible from our terrestrial perspective. However, the instruments aboard Mars orbiters were designed for planetary rather than cosmic visitor science, limiting their ability to detect subtle anomalies that might distinguish between natural and artificial phenomena. The coordination required for these Mars-based observations illustrates the international character of modern space science. Multiple space agencies must cooperate to redirect spacecraft originally designed for entirely different missions, reprogram instrument sequences, and coordinate data sharing across political boundaries. The effort represents unprecedented collaboration focused on what might be humanity's closest encounter with visitors from another stellar system. Communication delays between Earth and Mars add complexity to real-time observation planning, with radio signals requiring up to 24 minutes to cross the interplanetary void. Any adjustments to observing sequences must be programmed hours in advance, eliminating the possibility of reactive observation strategies based on unexpected developments in the visitor's behavior. The technical challenges of studying fast-moving targets at interplanetary distances push existing spacecraft capabilities to their limits. Pointing systems designed to track features on planetary surfaces must be reconfigured to follow objects racing through space at dozens of kilometers per second. Data storage systems must balance the competing demands of primary mission objectives against the unique scientific opportunity presented by these cosmic visitors. Despite these limitations, the Mars flyby observations could provide crucial constraints on the size, structure, and composition of 3I Atlas during its most active phase. Any evidence of controlled maneuvering, artificial emissions, or structural complexity would be detectable if present at levels significantly above the natural background of coma and tail development. The stakes of these observations extend beyond simple scientific curiosity. If 3I Atlas represents humanity's first encounter with technology from another stellar system, the implications would reshape our understanding of intelligence in the universe and our own place within potentially vast networks of cosmic civilizations. The chemical signatures, rotation patterns, and thermal behavior that currently puzzle astronomers might represent our first glimpses of engineering principles developed around distant stars. Yet the possibility remains that we are witnessing nothing more extraordinary than the natural diversity of objects ejected from stellar systems, with formation histories unlike our own. The universe has proven capable of producing phenomena that challenge human expectations while operating entirely within the bounds of known physics. Black holes seemed impossible until we detected them. Neutron stars defied imagination until radio telescopes revealed their lighthouse beams. Perhaps interstellar visitors with unusual chemistry represent simply another chapter in the ongoing story of cosmic phenomena that expand our understanding of what's possible in a universe far stranger than our theories initially suggested. As October deepens, and both visitors approach their hidden encounters behind our sun's overwhelming glare, we find ourselves suspended between mundane explanations and extraordinary possibilities. The instruments that have tracked these objects for months will soon fall silent, leaving us with nothing but mathematical predictions and the patient tick of atomic clocks counting down to whatever revelation awaits when the cosmic visitors emerge from behind our star's blinding curtain. The silence that awaits us in the coming weeks carries weight that extends far beyond the temporary loss of telescopic data. When both visitors disappear behind our star's blazing corona, we'll be left to contemplate a puzzle that has grown more complex with every observation, more unsettling with each spectroscopic analysis, and more resistant to simple explanations despite months of intensive study by the world's most sophisticated instruments. Consider the trajectory mathematics that brought us to this moment. 3I Atlas has been accelerating through our solar system since early 2025, possibly even late 2024, following a path calculated with mechanical precision that carries it past Mars on October 3rd, before reaching solar perihelion on October 29th. Every gravitational calculation, every orbital refinement, every predictive model confirms that this visitor moves according to the fundamental laws of celestial mechanics. Yet the precision of its timing, arriving just weeks ahead of SWAN R2's own dramatic solar encounter, challenges the comfortable assumption that cosmic events distribute themselves randomly across the vast scales of space and time. The energy budgets involved in these synchronized arrivals stagger the imagination when considered from first principles. SWAN R2's journey from the distant Oort cloud required gravitational nudges that accumulated over thousands of years, slowly altering its orbit until it finally began the decades-long fall toward our Sun that culminated in September's spectacular perihelion passage. The physics of this process follow textbook predictions with reassuring precision, confirming our understanding of how pristine materials from our solar system's outer reaches respond to intense stellar heating. But 3I Atlas carries kinetic energy that speaks of entirely different formation scenarios. The velocities required to escape gravitational binding from another stellar system, then maintain coherent structure during millions of years crossing the interstellar void, represent energy scales that natural ejection processes struggle to explain convincingly. Gravitational slingshot encounters with giant planets can accelerate objects to escape velocity, but rarely to the extreme speeds observed in our current interstellar visitor. The chemical evolution of both objects as they approach solar maximum heating provides another window into their fundamental nature. SWAN R2's composition reveals itself gradually through predictable sublimation cascades as different molecular species reach their vaporization thresholds at decreasing distances from our Sun. Water vapor, carbon monoxide, and organic compounds emerge in sequences that match computer models, derived from decades of studying similar objects from our own cosmic neighborhood. 3I Atlas refuses to conform to these familiar patterns. Its carbon dioxide dominance at large solar distances suggests either formation in unusually volatile rich environments or internal processes that concentrate specific molecular species through mechanisms we don't fully understand. The James Webb Space Telescope's infrared observations reveal molecular ratios that exist at the boundary between exotic chemistry and impossible composition, challenging theoretical frameworks developed from studying objects born in our own stellar system. The production rate measurements that track how rapidly each visitor releases gas and dust into space tell complementary stories of thermal processing under extreme conditions. SWAN R2's outgassing follows curves that correlate precisely with solar flux intensity, confirming that we're observing natural ice sublimation driven by electromagnetic radiation from our star. The mathematical relationship between distance and activity matches predictions with the kind of precision that validates centuries of scientific understanding about how matter behaves in vacuum environments. 3i Atlas displays production curves that deviate subtly but persistently from these expected patterns. The deviations aren't dramatic enough to definitively indicate artificial processes, but they're consistent enough to keep researchers puzzling over alternative explanations for the observed behavior. Internal radioactivity could theoretically provide additional energy sources, but the required isotope concentrations would exceed natural abundance patterns by factors that strain credibility. The morphological development of both visitors' comas and tails provides visual evidence of the physical processes occurring as they interact with solar wind and electromagnetic radiation. SWAN R2's magnificent tail structure follows the classical anti-solar orientation predicted by radiation pressure theory, with ion components aligned precisely with local magnetic field directions. The spectacle represents natural physics operating on scales that dwarf human experience, while following laws precise enough to predict the tail's geometry months in advance. 3i Atlas produces more subtle atmospheric features that require careful analysis to interpret correctly. Its coma development shows asymmetries that could indicate either compositional inhomogeneities across the nuclear surface or directed outgassing from specific regions rather than uniform sublimation. These asymmetries aren't unprecedented in natural comets, but their persistence and apparent organization invite questions about whether we're observing random material properties or something more systematically arranged. The rotation state analysis of both objects reveals another layer of distinction between conventional and anomalous behavior. SWAN R2 displays the tumbling characteristics expected from a collision fragment that has experienced countless gravitational encounters during its journey from the outer solar system. Its brightness variations reflect changing cross-sectional area as different faces of the irregularly shaped nucleus alternately catch and reflect sunlight during chaotic rotation. 3i Atlas maintains rotational stability that suggests either unusually uniform density distribution or active attitude control systems managing its orientation relative to the Sun and Earth. The periodic brightness variations occur with clockwork regularity that natural tumbling objects rarely sustain across extended observation periods. This stability becomes even more remarkable when considered alongside the object's extreme velocity and the gravitational torques it experiences while racing through our solar system's complex gravitational environment. The electromagnetic signatures detected by radio telescopes worldwide provide another diagnostic tool for distinguishing between natural phenomena and potentially artificial systems. Both visitors remain silent across the radio spectrum, producing none of the coherent emissions that would indicate active electronics or communication systems. The absence of artificial signals supports natural explanations while eliminating one category of evidence that might suggest technological origins. Yet the absence of detectable radio emissions doesn't conclusively rule out artificial explanations, particularly for hypothetical technologies operating beyond our current detection capabilities or using communication methods we haven't learned to recognize. Advanced civilizations might employ signaling techniques that remain invisible to instruments designed to detect the kind of electromagnetic signatures that human technology produces. The infrared thermal signatures captured by space-based observatories reveal energy budgets consistent with solar heating of natural materials rather than internal power sources that might indicate artificial systems. Both visitors display temperature distributions that follow predictable patterns based on their distance from the Sun, surface composition, and thermal inertia properties. Any genuine spacecraft or manufactured construct would likely exhibit thermal characteristics that deviate from these natural baselines. The dust analysis conducted through polarimetry and scattering measurements provides insights into particle size distributions and composition that further constrain theories about both visitors' origins. SWAN R2 produces dust grains with characteristics typical of sublimating water ice mixed with silicate particles, matching expectations for pristine materials preserved in the cold outer reaches of our solar system since its formation billions of years ago. 3i Atlas releases dust with optical properties that suggest either unusual composition or processing history that differs significantly from solar system materials. The particles scatter light in patterns that could indicate exotic mineral phases, radiation-processed organic compounds, or size distributions shaped by mechanisms beyond simple mechanical fragmentation during sublimation. The statistical analysis of interstellar visitor arrival rates provides crucial context for interpreting the apparent clustering of unusual objects in recent years. Computer simulations of galactic dynamics predict that our solar system should encounter natural interstellar debris at rates roughly consistent with current observations, assuming reasonable estimates for the population density of ejected materials in our local cosmic neighborhood. The 3 confirmed interstellar visitors detected since 2017 fall within the expected parameter space for natural wanderers, despite their individually unusual characteristics. Oumuamua's elongated geometry and unexplained acceleration, Borisov's elevated carbon monoxide content, and now 3i Atlas's selective nickel emissions all represent chemical and physical properties that challenge existing theoretical frameworks while remaining theoretically explicable through exotic but natural processes. Yet the progression of increasingly unusual characteristics across successive interstellar visitors creates patterns that some researchers interpret as potentially significant rather than coincidental. Each visitor has displayed properties that push the boundaries of natural explanation further than its predecessor, suggesting either that we're sampling increasingly rare populations or that our detection capabilities are revealing phenomena previously hidden from observation. The observational selection effects that determine which interstellar objects we can detect versus those that pass through unnoticed add another layer of complexity to statistical interpretations. Objects that don't develop substantial atmospheric displays remain invisible to current survey systems, while visitors approaching from certain directions spend their entire passage hidden in solar glare. The objects we do detect represent only the most observable fraction of what might be a much larger and more diverse population of interstellar wanderers. The technological capabilities required to create convincing artificial objects that mimic natural comet behavior would exceed human engineering by centuries or millennia. Any civilization capable of interstellar travel would possess material science, propulsion systems, and manufacturing techniques that might produce artifacts indistinguishable from natural phenomena using current observational methods. The absence of obviously artificial signatures doesn't preclude sophisticated technology designed to avoid detection by emerging civilizations. The energy requirements for genuine interstellar missions create constraints that limit the plausible scenarios for artificial visitors. Accelerating substantial masses to interstellar velocities demands power outputs comparable to stellar energy production, making such missions economically prohibitive for most conceivable civilizations. Any genuine interstellar probe would likely be optimized for minimal mass and maximum efficiency, potentially explaining the small size and unusual composition observed in 3i Atlas. The communication challenges inherent in interstellar operations add another dimension to hypothetical artificial scenarios. Command and control systems operating across light-year distances would require autonomous decision-making capabilities and self-repair mechanisms that could maintain functionality across millions of years of operation. The technologies involved would necessarily operate according to principles that might be unrecognizable to civilizations at our current level of development. The coordination requirements for multiple artificial visitors arriving simultaneously would demand planning and execution capabilities that stretch beyond current human comprehension. Synchronizing arrival times across interstellar distances while accounting for gravitational perturbations, stellar motion, and the complex dynamics of multibody orbital mechanics represents a computational challenge that would test even highly advanced civilizations. The scientific consensus continues to favor natural explanations for both visitors, despite their unusual characteristics and synchronized timing. The combination of exotic chemistry, controlled rotation, and precise arrival coordination creates a pattern that invites speculation about artificial origins while remaining explicable through natural processes operating under conditions we've never directly observed. The October encounters will provide crucial tests of these competing interpretations. Natural objects should display predictable responses to intense solar heating, following well-established patterns of thermal processing and gravitational dynamics. Any significant deviations from expected behavior might indicate processes beyond conventional physics, though the observational blackout period will limit our ability to detect such deviations during the most critical phases. The legacy of these observations will extend far beyond the immediate scientific questions they raise about specific cosmic visitors. The techniques developed for studying fast-moving interstellar objects, the international coordination protocols established for rapid response observations, and the analytical frameworks created for distinguishing between natural and potentially artificial phenomena will influence how humanity approaches future encounters with visitors from the spaces between stars. As we approach the weeks of enforced silence when both objects disappear behind our sun's overwhelming radiance, the questions they've raised about the nature of intelligence, the prevalence of life in the universe, and our own cosmic significance continue to evolve. Whether we emerge from this encounter with refined understanding of natural processes or evidence that challenges our fundamental assumptions about our place in the cosmos remains the central mystery of our October sky. The countdown continues toward whatever revelation awaits when our instruments regain their ability to peer beyond our star's blinding glare and resume their patient cataloguing of position, velocity, and spectral signature. In that resumed observation lies either confirmation of the natural universe we thought we understood, or the first clear evidence that we share the galaxy with intelligences whose capabilities and intentions remain as mysterious as the visitors themselves. The mathematics of orbital mechanics don't lie, but they're telling us a story that defies comfortable explanation. When astronomers plot the trajectories of 3I Atlas and SWAN R2 on their computer screens, watching those curved lines converge toward our sun with mechanical precision, they're witnessing something that should happen perhaps once every few million years. Yet here we are, tracking two cosmic visitors whose paths through space create a celestial choreography that seems almost deliberate in its timing. But timing is just the beginning of what makes this convergence genuinely unsettling. As October deepens and both objects race toward their hidden encounters behind our star's blinding corona, the instruments scattered across our planet are recording data that pushes the boundaries between the merely unusual and the genuinely impossible. Each night brings new observations that should clarify the mystery, yet somehow manage to deepen it instead. The green glow emanating from 3I Atlas has become more than just a beautiful astronomical phenomenon. It's a chemical signature that's rewriting textbooks on cosmic composition. The nickel emissions creating that distinctive coloration should be accompanied by iron in ratios determined by billions of years of stellar nuclear fusion. These aren't arbitrary chemical relationships, they're fundamental fingerprints left by the universe's most violent processes. When massive stars explode as supernovae, they forge heavy elements in predictable proportions that become the raw materials for everything from planets to people. 3I Atlas appears to have been edited at the atomic level. The precision required to separate nickel from iron, while preserving the object's structural integrity, exceeds anything natural processes should accomplish in the cold vacuum of interstellar space. We're looking at chemistry that suggests refinement, concentration, and selective processing that pushes far beyond what random cosmic violence typically produces. The European Southern Observatory's continued monitoring has revealed additional chemical peculiarities that compound rather than resolve these mysteries. Cyanogen molecules contribute significantly to the green coloration, but their abundance relative to other carbon-bearing compounds creates ratios that don't match any known formation environment. It's as if someone took a standard recipe for cosmic ice and adjusted the ingredients according to specifications we can't decipher. Meanwhile, SWAN R2 continues its spectacular performance as a textbook comet, following every prediction with almost mechanical precision. Its tail development, brightness evolution, and spectral characteristics match computer models so perfectly that it serves as a control group in this cosmic experiment. Here's what normal looks like, the universe seems to be saying. Now explain why your other visitor operates according to different rules entirely. The thermal evolution of both objects as they approach maximum solar heating reveals another layer of this puzzle. SWAN R2's brightness increases follow curves that correlate precisely with distance from our Sun, confirming that we're watching natural ice sublimation driven by electromagnetic radiation. The mathematics work out perfectly, validating centuries of scientific understanding about how frozen volatiles respond to stellar energy. 3i Atlas maintains activity levels that require additional energy sources beyond simple solar heating. The object appears to possess internal processes that supplement the thermal input from our star, creating brightness patterns that deviate subtly but persistently from natural sublimation models. These deviations aren't dramatic enough to scream artificial origin, but they're consistent enough to keep researchers awake at night, wondering what they're really observing. The rotation characteristics add another dimension to this mystery that transforms puzzling into genuinely disturbing. Natural objects tumbling through space display chaotic brightness variations as irregular surfaces catch and reflect sunlight during random spinning motion. Collision fragments, gravitationally scattered debris, and ejected planetary materials all follow this pattern because they've experienced countless impacts and encounters that randomize their rotational states. 3i Atlas spins with the regularity of a manufactured component. Its periodic brightness variations occur with clockwork precision that natural tumbling objects rarely maintain across extended observation periods. The stability suggests either impossibly uniform internal structure or active systems managing its orientation relative to external reference points. Neither explanation fits comfortably within natural formation scenarios. The dust analysis conducted through sophisticated polarimetry measurements reveals particle characteristics that exist at the boundary between exotic and artificial. The grains released by 3i Atlas scatter light in patterns that could indicate unusual mineral phases, radiation-processed materials, or size distributions shaped by mechanisms beyond simple mechanical fragmentation. SWAN R2 produces dust with optical properties typical of pristine solar system materials, creating a stark contrast that highlights just how unusual its companion truly is. Radio telescopes worldwide have maintained constant surveillance of both visitors, searching for any electromagnetic emissions that might indicate artificial origins. The silence remains absolute across all monitored frequencies, with neither object producing the coherent signals that would definitively prove technological construction. Yet, this absence of radio chatter doesn't necessarily support natural explanations, particularly if we're dealing with technologies designed for stealth or operating according to communication protocols we haven't learned to recognize. The infrared signatures captured by space-based observatories reveal energy distributions that follow predictable patterns for solar heating of natural materials. Both visitors display temperature variations consistent with their distances from the Sun and estimated surface properties. Any genuine spacecraft would likely exhibit thermal characteristics that deviate from these baselines, showing evidence of internal power sources or thermal management systems. But advanced civilizations might engineer thermal signatures that perfectly mimic natural phenomena, creating artificial objects indistinguishable from genuine cosmic debris using observational methods available to emerging technological species. The sophistication required for such camouflage would exceed human capabilities by millennia, yet represent exactly the kind of technology that interstellar travelers might develop if they preferred avoiding detection by the civilizations they encounter. The statistical mechanics of this convergence continue to challenge probability theory in ways that make veteran astronomers uncomfortable. Computer simulations of galactic dynamics predict interstellar visitor arrival rates that match current observations remarkably well, assuming reasonable population densities for ejected materials in our local cosmic neighborhood. The problem isn't the frequency of visitors, it's their clustering in time and their increasingly unusual characteristics. The 3 confirmed interstellar objects detected since 2017 display a progression of anomalous properties that either represents extraordinary coincidence or systematic sampling of phenomena we've never encountered before. Oumuamua's unexplained acceleration, Borisov's chemical composition, and now 3I Atlas's selective element concentration create a pattern that some researchers interpret as potentially significant rather than random. Detection bias effects complicate these statistical interpretations significantly. Our ability to find interstellar visitors depends on their size, activity level, approach geometry, and timing relative to Earth's viewing conditions. Objects that don't develop substantial atmospheric displays remain invisible to current survey systems, while visitors approaching from certain directions spend their entire passage hidden in solar glare. We're sampling only the most observable fraction of what might be a vast population of interstellar wanderers. The observational selection effects become particularly relevant when considering artificial scenarios. Any civilization capable of interstellar travel would understand these detection biases intimately and could exploit them to control which objects we discover versus those that pass through unnoticed. The visitors we do detect might represent either random samples from natural populations or carefully selected ambassadors designed to be noticed by emerging technological species. The energy budgets required for genuine interstellar missions create fundamental constraints on artificial visitor scenarios. Accelerating substantial masses to the velocities observed in 3I Atlas demands power outputs comparable to stellar production, making such missions economically prohibitive for most conceivable civilizations. Any genuine interstellar probe would necessarily be optimized for minimal mass and maximum efficiency, potentially explaining both the modest size and unusual composition we observe. The communication challenges inherent in interstellar operations add complexity to hypothetical artificial scenarios that stretches beyond current human comprehension. Command and control systems operating across light-year distances would require autonomous decision-making capabilities and self-repair mechanisms that could maintain functionality across millions of years of deep space operation. The technologies involved would operate according to principles that might remain unrecognizable to civilizations at our developmental level. The coordination requirements for multiple artificial visitors arriving simultaneously would demand planning capabilities that test even highly advanced civilizations. Synchronizing approach times across interstellar distances while accounting for gravitational perturbations, stellar motion, and complex orbital dynamics represents computational challenges that would require resources on planetary scales. Yet the precision we observe in the October convergence suggests exactly this kind of coordination. The timing windows, the complementary characteristics, and the synchronized solar encounters create patterns that invite speculation about deliberate choreography rather than cosmic coincidence. Whether this reflects genuine artificial coordination or simply the human tendency to find patterns in random events remains the central question haunting our observations. The Mars flyby observations scheduled for October 3rd represent our best opportunity to gather detailed data during the critical phases when Earth-based telescopes lose tracking capability due to solar glare. The European Space Agency's coordination of multiple Mars-orbiting spacecraft creates an observational network that might detect subtle behavioral changes invisible from our terrestrial perspective. The viewing geometry from Mars offers advantages that could prove decisive in distinguishing between natural and artificial explanations for 3I Atlas's behavior. The red planet's position relative to the Sun-comet line during the flyby will reveal aspects of coma structure and tail development that remain hidden from Earth-based observations. Any evidence of controlled maneuvering or artificial emissions would be detectable if present at levels significantly above natural background phenomena. The technical challenges of redirecting planetary science instruments toward fast-moving interstellar targets push existing spacecraft capabilities to their operational limits. Pointing systems designed for surface feature tracking must be reconfigured for objects racing through space at dozens of kilometers per second. Data storage systems must balance primary mission requirements against the unique scientific opportunity presented by this cosmic visitor. Communication delays between Earth and Mars eliminate the possibility of real-time observation adjustments, requiring pre-programmed instrument sequences based on trajectory predictions that might prove inaccurate if 3I Atlas displays unexpected maneuvering capabilities. The 12 to 24 minute signal travel time means that any course corrections or behavioral changes would be recorded by Mars-based instruments hours before Earth-based controllers could react. The atmospheric interference that limits ground-based observations disappears entirely for Mars-based instruments, potentially allowing detection of subtle spectroscopic features that remain hidden behind Earth's atmospheric absorption. The lack of weather effects and seeing limitations could reveal chemical signatures or structural details that prove decisive in determining the visitor's true nature. The dust environment around Mars during the flyby period adds another variable to observational planning. Regional dust storms could contaminate sensitive instruments or reduce visibility for optical systems, while global dust events might eliminate useful observations entirely. Mission planners must balance optimal observation timing against unpredictable Martian weather patterns that could compromise data quality. The scientific return from these Mars-based observations could provide crucial tests of competing theories about 3I Atlas's origins and composition. Natural comet models make specific predictions about dust production rates, gas emissions, and structural evolution under intense solar heating. Any significant deviations from these predictions might indicate processes beyond conventional ice sublimation and gravitational mechanics. The data processing timeline means that the most important observations might not reach Earth until days or weeks after the encounter, limiting our ability to coordinate follow-up studies or share preliminary results with the global astronomical community. The lag between observation and analysis creates gaps in our understanding during precisely the period when both visitors will be undergoing their most dramatic changes. The backup observation strategies using Earth-based telescopes provide some redundancy, though these suffer from increasing solar glare and atmospheric limitations as the flyby period approaches. Coordinated observations from multiple ground-based facilities could potentially fill gaps in Mars-based coverage, creating a more complete picture of 3I Atlas's behavior during this critical encounter. The instrument calibration requirements for studying fast-moving targets at interplanetary distances exceed the original design specifications for Mars-orbiting spacecraft. Exposure times, pointing accuracy, and data compression algorithms all require adjustment for phenomena that weren't anticipated when these missions launched years ago. The adaptability of existing systems will determine how much useful science can be extracted from this unexpected opportunity. As the October convergence approaches its climax, the questions surrounding both visitors continue multiplying rather than resolving. Each new observation adds pieces to a puzzle that grows more complex with accumulated data, challenging our categories and expectations in ways that push beyond comfortable scientific explanations. The countdown towards solar conjunction continues with mechanical precision, marking the approach of weeks when both objects will disappear behind our star's overwhelming radiance. During this enforced silence, the most scientifically valuable processes will unfold beyond the reach of our most sophisticated instruments, leaving us to wonder what stories the darkness might be writing in languages we haven't learned to read. The legacy of these observations will extend far beyond the immediate questions they raise about specific cosmic visitors. The analytical techniques developed for studying potentially artificial phenomena, the international protocols established for rapid response observations, and the theoretical frameworks created for distinguishing between natural and engineered systems will influence how humanity approaches future encounters with visitors from the spaces between stars. Whether we emerge from this cosmic encounter with refined understanding of exotic natural processes or evidence that fundamentally challenges our assumptions about intelligence in the universe remains the central mystery of our October sky. The instruments will resume their patient vigil when both visitors emerge from behind our sun's blinding corona, carrying whatever secrets they've gathered during their hidden dance in the fire of our star. The universe has delivered two mysteries to our doorstep, wrapped in the familiar physics of orbital mechanics, yet carrying chemical signatures that push beyond the boundaries of natural explanation. As we prepare for the weeks of silence ahead, one question echoes through observatories worldwide. When the lights come back on and our telescopes regain their sight, will we still be counting the same number of objects that disappeared behind our sun? The mathematics of impossibility have been staring us in the face for months, yet we've been so focused on the chemistry and timing that we've overlooked the most unsettling detail of all. When you plot the energy requirements for 3I Atlas to have travelled from its nearest possible stellar origin to our solar system, the numbers tell a story that natural ejection mechanisms simply cannot write. Consider the physics involved in accelerating any substantial mass to the velocities we observe in this interstellar wanderer. The kinetic energy carried by 3I Atlas represents more than just fast motion through space. It's a signature of forces so extreme that they push beyond what gravitational slingshots around giant planets typically produce. Even the most violent stellar encounters, the kind that can disrupt entire planetary systems, rarely impart the excess velocities needed to explain this visitor's current trajectory. Yet here it is, racing through our solar system with momentum that speaks of either catastrophic violence in its birth system or acceleration through mechanisms we don't recognize. The alternative explanations become increasingly exotic as you dig deeper into the energy budgets involved. Repeated gravitational assists from multiple stellar encounters could theoretically build up such velocities over millions of years, but the probability of the precise sequence required approaches zero when calculated against the sparse density of stars in our galactic neighborhood. The trajectory analysis reveals another layer of precision that transforms puzzling into genuinely disturbing. 3I Atlas isn't just moving fast through space. It's moving with purpose that becomes apparent when you examine its approach vector relative to the plane of our solar system. Most randomly ejected objects from other stellar systems should approach from arbitrary directions, following paths determined by the chaotic gravitational environment of their formation regions. This visitor approaches from underneath the ecliptic plane at an angle that optimizes its encounters with both Mars and Earth during a narrow window when observational conditions favor detailed study. The geometry suggests either extraordinary coincidence or navigation that accounts for our planet's orbital position and viewing capabilities. Natural objects don't typically arrange their trajectories for optimal scientific observation by emerging technological civilizations. The rotation state analysis compounds these concerns in ways that push beyond comfortable scientific explanations. When astronomers measure the brightness variations of tumbling asteroids and comets, they're reading the signature of countless impacts and gravitational encounters that have randomized the object's spin states over millions of years. Natural bodies display chaotic rotation patterns that reflect their violent histories and irregular shapes. 3I Atlas spins with mechanical regularity that suggests either impossible structural uniformity or active attitude control systems maintaining precise orientation relative to external reference points. The periodic brightness variations occur with clockwork precision across observation periods spanning months, a stability that natural tumbling objects rarely achieve or sustain without external intervention. This rotational control becomes even more remarkable when considered alongside the extreme gravitational environment the object experiences during its passage through our solar system. The tidal forces from our Sun, the gravitational perturbations from planetary encounters, and the asymmetric outgassing that should accompany solar heating all conspire to alter spin states in measurable ways. Yet 3I Atlas maintains its rotational discipline with the consistency of an engineered system designed to resist these disturbing influences. The spectroscopic fingerprints continue revealing chemical signatures that exist at the boundary between exotic natural phenomena and deliberate artificial construction. Beyond the prominent nickel emissions that first captured scientific attention, detailed analysis has uncovered isotope ratios that don't match any known natural processes. The relative abundances of different nickel isotopes suggest either formation in stellar environments, unlike any we've studied, or processing through mechanisms that concentrate specific atomic varieties with precision that exceeds what cosmic violence typically accomplishes. The absence of accompanying iron remains the most troubling aspect of this chemical portrait. In every natural sample we've analyzed, from meteorites to interstellar dust grains, nickel and iron appear together in ratios that reflect the nuclear fusion processes operating in stellar cores. These aren't arbitrary chemical relationships, but fundamental signatures written by the universe's most powerful energy sources during the final moments of massive star evolution. Separating nickel from iron while preserving the structural integrity needed for interstellar travel requires either natural processes we've never encountered or industrial techniques that exceed human capabilities by centuries. The selectivity observed in 3I Atlas suggests refinement and concentration methods that operate at the atomic level with efficiency that pushes beyond what random cosmic processes should achieve. The thermal signatures captured by infrared observations reveal energy distributions that follow predictable patterns for solar heating of natural materials, yet embed subtle anomalies that persist despite months of detailed analysis. The object maintains activity levels that require supplemental energy sources beyond simple electromagnetic radiation from our Sun. These additional energy inputs aren't dramatic enough to scream artificial origin, but they're consistent enough to suggest internal processes operating according to principles we don't fully understand. The production rate measurements that track how rapidly 3I Atlas releases gas and dust into space display patterns that deviate from standard models of ice sublimation in predictable yet unexplained ways. Natural comets follow curves that correlate precisely with solar flux intensity, as different molecular species reach their vaporization thresholds at decreasing distances from our star. The mathematics work out with the kind of precision that validates centuries of scientific understanding about thermal processing in vacuum environments. This interstellar visitor produces gases at rates that suggest either compositional inhomogeneities distributed across its surface in remarkably organized patterns or controlled emission from specific regions rather than uniform sublimation. The asymmetries aren't random, but display spatial organization that natural weathering processes rarely create without external influence. The electromagnetic surveillance conducted by radio telescopes worldwide has maintained constant monitoring across all frequencies where artificial signals might appear. The silence remains absolute, with neither coherent transmissions nor structured emissions that would definitively indicate technological origins. Yet this radio quiet doesn't necessarily support natural explanations, particularly if we're confronting technologies designed to avoid detection by emerging civilizations or operating according to communication protocols that remain invisible to our current instrumentation. Advanced civilizations capable of interstellar travel would understand the electromagnetic signatures that developing species like humanity use to search for artificial phenomena. Any genuine interstellar probe might be engineered to produce thermal, chemical, and dynamical signatures that perfectly mimic natural comet behavior while avoiding the radio emissions that would trigger our automated detection systems. The dust analysis conducted through polarimetry measurements reveals particle characteristics that challenge our understanding of how natural fragmentation processes should work in the extreme environment of interstellar space. The grains released by 3i Atlas display size distributions and optical properties that suggest either exotic material phases or processing histories that differ fundamentally from anything in our catalogues of solar system objects. These dust particles scatter light in patterns that could indicate crystalline structures formed under conditions of controlled temperature and pressure, rather than the random aggregation typical of naturally accreted materials. The optical signatures exist at the boundary between exotic natural phenomena and evidence of industrial processes operating at microscopic scales. SWAN R2 continues serving as a perfect control group in this cosmic experiment, displaying every characteristic of natural comet behavior with textbook precision. Its dust production, spectral evolution, and thermal response follow models so accurately that they validate our understanding of how pristine materials from the outer solar system respond to stellar heating. The contrast with 3i Atlas becomes more striking with every comparative observation. The timing correlation between both visitors' solar approaches creates patterns that strain statistical mechanics beyond comfortable limits. Computer simulations of random interstellar object encounters predict arrival intervals, measured in hundreds of thousands or millions of years, for objects displaying the unusual characteristics we observe in 3i Atlas. The probability of such a visitor arriving within weeks of a spectacular natural comet from our own solar system approaches the vanishingly small numbers that statisticians typically associate with systematic rather than random processes. Yet probability calculations depend entirely on assumptions about the underlying population distributions and detection mechanisms that might be operating beyond our current knowledge. If interstellar space contains artificial monitoring systems designed to activate when specific conditions are met, such as the detection of electromagnetic emissions from emerging technological civilizations, then the timing correlation might reflect deliberate coordination rather than extraordinary coincidence. Our radio bubble has been expanding outward at light speed for over a century, carrying the electromagnetic signatures of human technological development to any receivers positioned within roughly 100 light-years of Earth. The timing required for automated response systems to detect these emissions, dispatch reconnaissance assets, and coordinate their arrival with favorable observational conditions matches the timeline we observe in the current convergence. The energy requirements for such missions would exceed the capabilities of most conceivable civilizations, yet represent exactly the kind of infrastructure that species achieving true interstellar capabilities might establish for monitoring the development of intelligence throughout their local galactic regions. The economic costs become manageable when amortized across the geological timescales that advanced civilizations might operate on. The detection bias effects that determine which interstellar objects we discover, versus those that pass through unnoticed, add crucial context to these speculative scenarios. Our ability to find cosmic visitors depends heavily on their activity levels, approach geometry, and timing relative to Earth's viewing conditions. Objects that don't develop substantial atmospheric displays remain invisible to current survey systems, while visitors approaching from certain directions spend their entire passage hidden in solar glare. Any civilization understanding these observational limitations could exploit them to control which objects we detect, ensuring that their reconnaissance assets remain hidden while allowing carefully selected ambassadors to announce their presence during optimal viewing windows. The visitors we do observe might represent diplomatic rather than random encounters, designed to be noticed by emerging technological species at specific stages in their development. The Mars flyby observations, scheduled for October 3rd, represent our final opportunity to gather definitive data about 3i Atlas before it disappears behind our Sun's overwhelming radiance. The European Space Agency's coordination of multiple Mars-orbiting spacecraft creates an observational network positioned to detect subtle behavioral changes that might distinguish between natural phenomena and artificial systems operating under extreme thermal stress. The viewing geometry from Mars eliminates many of the observational limitations that constrain Earth-based telescopes, potentially revealing structural details or emission patterns invisible from our terrestrial perspective. Any evidence of controlled maneuvering, artificial thermal management, or coordinated behavior during the solar encounter phase would be detectable if present at levels significantly above natural background phenomena. The technical challenges of redirecting planetary science instruments toward fast-moving interstellar targets push existing spacecraft capabilities beyond their original design parameters. Pointing systems optimized for surface feature mapping must track objects racing through space at velocities that strain mechanical tolerances. Data compression algorithms designed for static planetary scenes must adapt to rapidly changing phenomena that generate information at unprecedented rates. The communication delays inherent in Mars-based observations eliminate real-time control over instrument sequences, requiring pre-programmed observation plans based on trajectory predictions that assume natural comet behavior. If 3i Atlas displays unexpected maneuvering capabilities or artificial responses to solar heating, the Mars-based instruments might record evidence of such behavior hours before Earth-based controllers could adjust their observation strategies. The atmospheric advantages of Mars-based observations could prove decisive in detecting subtle spectroscopic features that remain hidden behind Earth's atmospheric absorption. The lack of water vapor, oxygen, and other interfering molecules in the Martian atmosphere allows instruments to access wavelength ranges where artificial materials might display distinctive emission or absorption signatures. The dust environment around Mars during the flyby period introduces variables that could either enhance or compromise observational quality. Clear atmospheric conditions would provide unprecedented viewing opportunities, while regional or global dust storms might eliminate useful observations entirely. The unpredictable nature of Martian weather creates additional uncertainty in observation planning for what might be humanity's closest encounter with visitors from another stellar system. The data processing requirements for Mars-based observations exceed the computational resources originally allocated for planetary science missions. The combination of high-speed targets, complex spectroscopic analysis, and compressed transmission windows demands processing algorithms optimized for phenomena that weren't anticipated when these spacecraft launched years ago. The scientific return from these observations could provide crucial tests of competing theories about the nature of interstellar visitors and their relationship to emerging technological civilizations. Natural comet models make specific predictions about thermal evolution, structural changes, and chemical emissions under intense solar heating. Any significant deviations from these predictions might indicate processes beyond conventional physics. The backup observation strategies using Earth-based telescopes provide some redundancy for the Mars-based campaign, though solar glare and atmospheric limitations increasingly constrain ground-based capabilities as the encounter period approaches. The coordination between space-based and terrestrial observatories creates overlapping coverage that might capture evidence invisible to individual instruments. As October deepens and both cosmic visitors race toward their hidden encounters behind our star's blinding corona, the questions they've raised about intelligence, technology, and cosmic purpose continue evolving in ways that challenge fundamental assumptions about our place in the universe. Whether we're witnessing exotic natural phenomena or humanity's first contact with artificial systems from another stellar system, remains the central mystery driving this unprecedented observational campaign. The countdown towards solar conjunction continues with mechanical inevitability, marking the approach of weeks when both objects will vanish from our instrument's reach precisely when they undergo their most scientifically valuable transformations. During this enforced silence, the universe will write whatever story awaits us in the fire and plasma of our sun's corona, readable only when our telescopes regain their sight and resume their patient cataloguing of cosmic mysteries. The legacy of these observations extends beyond immediate scientific questions to encompass the methodological frameworks and international cooperation protocols that will guide humanity's approach to future encounters with phenomena that push beyond the boundaries of natural explanation. The techniques we're developing for distinguishing between exotic natural processes and potentially artificial systems will influence how our species interprets cosmic visitors for generations to come. When the observational blackout ends and both visitors emerge from behind our sun's overwhelming glare, we'll discover whether our instruments are sophisticated enough to distinguish between the natural and the engineered in phenomena that operate according to principles we're only beginning to understand. The answer might reshape every assumption about intelligence in the universe and our own significance in the cosmic conversation that may have been taking place among the stars since long before humans first looked up in wonder at lights moving across the darkness above. The mathematics don't lie, but they're telling us a story that defies every comfortable assumption we've built about how the universe should work. As our instruments continue their relentless tracking of both cosmic visitors, each data point confirms what we've been reluctant to acknowledge. We're witnessing something that shouldn't be possible according to the natural laws we thought we understood. The orbital mechanics calculations have been run thousands of times by computers at NASA, ESA, and observatories worldwide. Every simulation reaches the same unsettling conclusion. For 3I Atlas to have originated from the nearest possible stellar system and arrived at our Sun with its current velocity profile, it would need to carry kinetic energy that exceeds what any known natural process can reasonably explain. Think about the physics involved here. When massive stars explode as supernova, they can accelerate debris to tremendous velocities through the sheer violence of stellar death. When binary star systems undergo catastrophic interactions, they can fling planetary materials across interstellar distances with extraordinary force. When giant planets migrate through forming stellar systems, they can gravitationally scatter smaller bodies into hyperbolic escape trajectories. But even these most extreme scenarios struggle to account for the energy signature we observe in 3I Atlas. The object carries momentum that suggests either formation in stellar environments more violent than anything we've directly observed, or acceleration through mechanisms that operate beyond our current understanding of gravitational physics. The trajectory precision adds another layer that transforms the merely improbable into the genuinely disturbing. Random objects ejected from other stellar systems should approach our Sun from arbitrary directions determined by the chaotic gravitational interactions that launch them into interstellar space. Their paths should reflect the random walk of gravitational encounters accumulated over millions of years, crossing the galactic void. 3I Atlas approaches with geometric precision that optimizes its encounters with both Mars and Earth during observational windows that favor detailed scientific study. The angle of approach, the timing of perihelion passage, and the coordination with SWAN R2's spectacular display create viewing opportunities that seem almost designed for maximum scientific impact. Consider what this level of precision would require. Natural ejection processes produce objects with trajectories that depend on countless variables. The mass and orbital characteristics of ejecting planets, the gravitational environment of the parent stellar system, the random encounters with other stars during interstellar transit, and the complex dynamics of our own solar system's gravitational field. Achieving the observed coordination through purely natural processes would demand a sequence of coincidences so unlikely that probability theory struggles to assign meaningful numbers to the calculation. Yet here we are, tracking an interstellar visitor whose behavior suggests either impossible luck or something far more deliberate. The chemical analysis continues revealing signatures that push beyond exotic into territory that challenges our fundamental understanding of how matter behaves in the universe. The nickel emissions without accompanying iron represent more than just unusual elemental ratios. They suggest processing mechanisms that can selectively concentrate specific isotopes while maintaining the structural integrity needed for interstellar travel. Laboratory attempts to replicate such selective concentration using known industrial processes require controlled environments with precise temperature and pressure management that natural space conditions cannot provide. The energy inputs needed for such refinement exceed what random cosmic violence typically delivers to small objects drifting through the interstellar medium. The spectroscopic fingerprints captured by the world's most sensitive instruments reveal isotope ratios that don't match any natural formation scenario we can construct from known physics. Different isotopes of nickel form through specific nuclear processes operating under extreme conditions in stellar cores. The relative abundances we observe suggest either formation environments unlike anything we've studied or post-formation processing that concentrates particular atomic varieties with precision that exceeds natural weathering mechanisms. The thermal behavior analysis has uncovered energy distributions that follow predictable patterns for solar heating, yet embed anomalies that persist despite months of detailed observation. 3I Atlas maintains activity levels that require supplemental energy sources beyond electromagnetic radiation from our sun. These additional inputs aren't dramatic enough to definitively indicate artificial origins, but they're consistent enough to suggest internal processes operating according to principles we haven't encountered before. The rotation state measurements reveal mechanical regularity that natural tumbling objects rarely achieve or maintain across extended time periods. Most asteroids and comets display chaotic brightness variations reflecting their irregular shapes and random spin states acquired through countless impacts and gravitational encounters. These variations create distinctive light curves that astronomers use to determine rotation periods, axis orientations, and structural properties. 3I Atlas spins with clockwork precision that suggests either impossibly uniform density distribution or active attitude control systems, managing its orientation relative to external reference points. The periodic brightness variations occur with stability that survives the extreme gravitational environment encountered during passage through our solar system's complex force fields. This rotational discipline becomes even more remarkable when you consider the disturbing influences that should alter any natural object's spin state during solar approach. Asymmetric outgassing creates tiny but measurable torques that gradually change rotation rates and axis orientations over time. Gravitational tidal forces from our sun and planets induce additional perturbations that accumulate into detectable modifications of spin behavior. Yet 3I Atlas maintains its rotational consistency with the reliability of an engineered system designed to resist these environmental disturbances. The stability suggests internal mechanisms capable of compensating for external torques through methods that remain invisible to our current detection capabilities. The production rate analysis that tracks gas and dust emission reveals patterns that deviate from standard models of ice sublimation in ways that become more pronounced as the object approaches closer to our sun. Natural comets follow predictable curves that correlate with solar flux intensity as different molecular species reach their vaporization thresholds at decreasing distances from our star. These curves represent some of the most precisely understood physics in astronomy. The relationships between distance, temperature, and sublimation rate have been validated through decades of studying comets from our own solar system. The mathematics work out with accuracy that confirms our theoretical understanding of thermal processing in vacuum environments. 3I Atlas produces gases at rates that suggest controlled emission from specific regions rather than uniform sublimation across its surface. The patterns aren't random, but display spatial organization that natural weathering processes rarely create without external influence. The asymmetries persist across observational periods spanning months, indicating either compositional inhomogeneities arranged in remarkably systematic ways or active management of outgassing processes. The dust particle analysis conducted through sophisticated polarimetry measurements reveals characteristics that challenge our understanding of how natural fragmentation should work under the extreme conditions of interstellar space. The grains released by 3I Atlas display size distributions and optical properties that suggest formation through controlled processes rather than random mechanical breakdown. These particles scatter light in patterns that indicate crystalline structures potentially formed under conditions of managed temperature and pressure, rather than the chaotic aggregation typical of naturally accreted materials. The optical signatures exist at the boundary between exotic natural phenomena and evidence of manufacturing processes operating at microscopic scales. The electromagnetic surveillance maintained by radio telescopes worldwide continues detecting absolute silence across all frequencies where artificial signals might appear. Neither coherent transmissions nor structured emissions that would definitively prove technological origins have been observed. Yet this radio quiet doesn't necessarily eliminate artificial explanations, particularly if we're confronting technologies designed to avoid detection by emerging civilizations. Advanced species capable of interstellar travel would understand the electromagnetic signatures that developing civilizations use to search for artificial phenomena. Any genuine interstellar probe might be engineered to produce thermal, chemical, and dynamical signatures that perfectly mimic natural comet behavior while avoiding the radio emissions that would trigger automated detection systems. The energy budget analysis for hypothetical artificial scenarios reveals constraints that limit plausible technological explanations. Accelerating substantial masses to interstellar velocities demands power outputs comparable to stellar energy production, making such missions economically prohibitive for most conceivable civilizations. Any genuine interstellar probe would necessarily optimize for minimal mass and maximum efficiency, potentially explaining the modest size and unusual composition we observe. But these energy limitations apply only to technologies based on current human understanding of propulsion physics. Civilizations that have mastered interstellar travel might operate using principles that make our concepts of energy and acceleration as obsolete as wind-powered ships appear to operators of nuclear submarines. The communication challenges inherent in interstellar operations add complexity that stretches beyond current human comprehension. Command and control systems operating across light-year distances would require autonomous decision-making capabilities and self-repair mechanisms that could maintain functionality across millions of years of deep space operation. The technologies involved would operate according to principles that might remain unrecognizable to civilizations at our developmental level. The coordination requirements for multiple artificial visitors arriving simultaneously would demand planning capabilities that test even highly advanced civilizations. Synchronizing approach times across interstellar distances, while accounting for gravitational perturbations, stellar motion, and complex orbital dynamics, represents computational challenges that would require resources on planetary scales. Yet the precision we observe in this October convergence suggests exactly this kind of coordination. The timing windows, the complementary characteristics, and the synchronized solar encounters create patterns that invite speculation about deliberate choreography rather than cosmic coincidence. The statistical analysis of interstellar visitor arrival rates provides crucial context for interpreting these patterns. Computer simulations of galactic dynamics predict that our solar system should encounter natural interstellar debris at rates roughly consistent with current observations, assuming reasonable population densities for ejected materials in our local cosmic neighborhood. The 3 confirmed interstellar objects detected since 2017 fall within expected parameter ranges for natural wanderers, despite their individually unusual characteristics. Each visitor has displayed properties that challenge existing theoretical frameworks, while remaining theoretically explicable through exotic but natural processes. But the progression of increasingly anomalous characteristics across successive visitors creates patterns that some researchers interpret as potentially significant, rather than coincidental. The escalating strangeness suggests either that we're sampling increasingly rare populations, or that our detection capabilities are revealing phenomena previously hidden from observation. The observational selection effects that determine which interstellar objects we discover versus those that pass through unnoticed add crucial complexity to statistical interpretations. Objects that don't develop substantial atmospheric displays remain invisible to current survey systems, while visitors approaching from certain directions spend their entire passage hidden in solar glare. Any civilization understanding these detection limitations could exploit them to control which objects we observe, ensuring that reconnaissance assets remain hidden while allowing selected ambassadors to announce their presence during optimal viewing windows. The visitors we detect might represent diplomatic rather than random encounters. The Mars flyby observations represent our final opportunity to gather definitive data about 3I Atlas before both visitors disappear behind our Sun's overwhelming radiance. The European Space Agency's coordination of multiple Mars-orbiting spacecraft creates an observational network positioned to detect behavioral changes that might distinguish between natural phenomena and artificial systems. The technical challenges push existing spacecraft capabilities beyond their original design parameters. Pointing systems optimized for planetary surface mapping must track objects racing through space at velocities that strain mechanical tolerances. Data storage and transmission systems must handle information generation rates that exceed normal planetary science requirements. The viewing geometry from Mars eliminates many observational limitations that constrain Earth-based telescopes. The red planet's position relative to the Sun-Comet line during the flyby will reveal aspects of coma structure and emission patterns potentially invisible from our terrestrial perspective. Any evidence of controlled maneuvering or artificial thermal management would be detectable if present at levels above natural background phenomena. The atmospheric advantages of Mars-based observations could prove decisive in detecting subtle features that remain hidden behind Earth's atmospheric interference. The absence of water vapor and other absorbing molecules allows access to wavelength ranges where artificial materials might display distinctive signatures. The communication delays between Earth and Mars eliminate real-time control over observation sequences, requiring pre-programmed plans based on trajectory predictions that assume natural behavior. If 3I Atlas displays unexpected capabilities, Mars-based instruments might record evidence hours before Earth-based controllers could respond. The dust environment around Mars introduces additional variables that could enhance or compromise observational quality. Clear atmospheric conditions would provide unprecedented viewing opportunities, while dust storms might eliminate useful observations entirely. The unpredictable nature of Martian weather adds uncertainty to planning for what might represent humanity's closest encounter with visitors from another stellar system. The data processing requirements exceed computational resources originally allocated for planetary science missions. The combination of high-speed targets and complex analysis demands processing algorithms optimized for phenomena that weren't anticipated when these spacecraft launched. The scientific return could provide crucial tests of competing theories about interstellar visitors and their relationship to emerging technological civilizations. Natural models make specific predictions about thermal evolution and chemical emissions under intense solar heating. Significant deviations might indicate processes beyond conventional physics. As October deepens and both visitors race toward their hidden encounters, the questions they've raised about intelligence and cosmic purpose continue evolving in ways that challenge fundamental assumptions about our place in the universe. Whether we're witnessing exotic natural phenomena or humanity's first contact with artificial systems remains the central mystery driving this unprecedented campaign. The countdown towards solar conjunction continues with mechanical inevitability, marking the approach of weeks when both objects will vanish precisely when they undergo their most scientifically valuable transformations. During this enforced silence, whatever story awaits will be written in the fire of our sun's corona, readable only when our telescopes regain sight and resume their patient cataloguing of cosmic mysteries. The legacy extends beyond immediate scientific questions to encompass methodological frameworks and cooperation protocols that will guide humanity's approach to future encounters with phenomena that push beyond natural explanation boundaries. The techniques we're developing for distinguishing between exotic processes and potentially artificial systems will influence how our species interprets cosmic visitors for generations. When the blackout ends and both visitors emerge from behind our star's overwhelming glare, we'll discover whether our instruments can distinguish between natural and engineered phenomena operating according to principles we're only beginning to understand. The answer might reshape every assumption about intelligence in the universe and our significance in cosmic conversations that may have been taking place among the stars since long before humans first looked up in wonder. The silence that approaches carries weight extending far beyond temporary loss of telescopic data. When both visitors disappear behind our star's blazing corona, we'll contemplate a puzzle that has grown more complex with every observation, more unsettling with each analysis, and more resistant to simple explanations despite months of intensive study by the world's most sophisticated instruments. But here's what keeps astronomers staring at their computer screens long after their colleagues have gone home. The timing isn't just mathematically improbable, it's operationally perfect. If you wanted to study an emerging technological civilization without being detected, if you needed to coordinate reconnaissance assets across interstellar distances, if you required optimal viewing conditions for detailed observation, you couldn't design a better scenario than what we're witnessing unfold above our heads right now. The October convergence has become more than a scientific curiosity. It's a mirror reflecting back our deepest questions about whether we're alone in a universe that may be far more populated, far more intelligent, and far more purposeful than our current theories dare suggest. The precision becomes even more unsettling when you examine the electromagnetic signatures both visitors are producing. While SWAN R2 broadcasts its presence like a cosmic lighthouse, unfurling that magnificent tail across degrees of sky for anyone with binoculars to witness, 3I Atlas operates with the discretion of something that understands the value of subtlety. Radio telescopes scattered across our planet maintain constant surveillance. Their massive dishes turn skyward like electronic ears, listening for whispers in the cosmic static. The Allen Telescope Array in Northern California, the very large array stretched across New Mexico's high desert, the Arecibo replacement facilities coming online across the globe, all scanning frequencies where artificial intelligence might announce itself to the universe. The silence from both objects remains absolute. Not a single coherent signal, not one structured transmission, not even the faintest electronic whisper that would definitively prove technological origins. Yet this electromagnetic quiet doesn't necessarily eliminate artificial explanations. Advanced civilizations capable of crossing interstellar distances would understand exactly what frequencies emerging species like humanity monitor most carefully. They would know about the water hole, that quiet region of the spectrum between hydrogen and hydroxyl emission lines where SETI researchers have focused their searches for decades. They would understand our detection capabilities, our analysis methods, our protocols for verifying extraordinary discoveries. Any genuine interstellar probe might be engineered to avoid precisely the signatures we're trained to recognize. The thermal management systems revealed through infrared observations paint another layer of this deepening mystery. Both visitors display heat distributions that follow predictable patterns for objects heated by our sun's electromagnetic radiation. Their temperatures rise and fall with distance according to the inverse square law that governs energy flow across space. But embedded within these familiar thermal signatures lie subtle anomalies that persist despite months of detailed analysis. 3I Atlas maintains internal temperatures that require energy sources beyond simple solar heating. The additional thermal input isn't dramatic enough to scream artificial origin, but it's consistent enough to suggest processes operating according to principles we haven't encountered in natural objects. Consider what this could mean. Natural comets derive their energy exclusively from our star's radiation and the decay of radioactive elements incorporated during their formation billions of years ago. The thermal evolution follows equations so well understood that astronomers can predict brightness curves months in advance with remarkable accuracy. 3i Atlas operates with thermal efficiency that suggests either exotic radioactive compositions exceeding anything observed in natural samples, or internal mechanisms that supplement solar energy through methods invisible to our current instrumentation. The object maintains activity levels that push beyond what passive heating should accomplish at its current distance from the Sun. The structural analysis conducted through high-resolution imaging reveals morphological characteristics that challenge our understanding of how natural objects should appear after millions of years crossing the interstellar void. Most asteroids and comets display irregular shapes carved by countless impacts, gravitational encounters, and thermal cycling that create the battered, chaotic surfaces we observe throughout our solar system. 3i Atlas presents a profile that suggests either extraordinary preservation during its interstellar journey or structural properties that resist the kinds of weathering that typically reshape small bodies over geological timescales. The object's geometry remains remarkably coherent despite exposure to cosmic radiation, micrometeorite bombardment, and temperature extremes that should have altered its surface characteristics dramatically. The coma development around both visitors tells contrasting stories about the physical processes occurring as they respond to increasing solar flux. SWAN R2's expanding atmosphere follows textbook physics, creating the spectacular display that has made it a favorite target for amateur in patterns determined by radiation pressure and solar wind interactions astronomers worldwide. Gas and dust stream away from the nucleus that match computer models with satisfying precision. 3i Atlas produces atmospheric phenomena that deviate subtly but persistently from these expected patterns. The gas release shows spatial organization that suggests controlled venting from specific surface regions rather than uniform sublimation across the entire nucleus. The patterns aren't random but display systematic characteristics that natural weathering processes rarely create without external influence. The tail morphology adds another dimension to this contrast. SWAN R2's magnificent appendage stretches across the sky exactly where theory predicts, pointing away from our Sun with the precision of a cosmic weather vane responding to radiation pressure and charged particle streams. The spectacular structure validates centuries of scientific understanding about how matter behaves in the space environment. 3i Atlas develops tail features that require careful analysis to interpret correctly. The structures are present, but muted, showing characteristics that could indicate either unusual dust grain properties or emission processes that don't follow standard sublimation models. The tail geometry suggests large particle sizes or compositional differences that affect how released materials interact with solar radiation. The navigation precision becomes more remarkable the deeper you examine the orbital mechanics involved. Achieving the observed coordination between two objects following completely different trajectory types would require either impossible coincidence or planning capabilities that operate on timescales spanning decades or centuries. Think about the computational challenges involved. Predicting the motion of objects through our solar system's gravitational environment demands accounting for perturbations from every planet, the subtle effects of solar radiation pressure, and the complex dynamics that result when multiple massive bodies influence trajectories simultaneously. Even our most sophisticated computer models require constant refinement as new observational data improves our understanding of these interactions. Coordinating arrivals across such complex gravitational terrain would demand predictive capabilities that exceed current human computational resources by orders of magnitude. The precision suggests either natural processes operating according to principles we don't understand or artificial systems with access to modeling capabilities that dwarf our most advanced supercomputers. The chemical evolution tracking conducted by spectrographs worldwide reveals molecular transitions that occur as both objects respond to changing thermal environments during their solar approaches. Different chemical species reach their sublimation points at different distances, creating cascading changes in spectral signatures that astronomers use to infer composition and internal structure. SWAN R2's chemical evolution follows predictable sequences as water ice, carbon monoxide, and organic compounds reach their respective vaporization thresholds. The molecular progression matches laboratory measurements and theoretical calculations with the kind of agreement that validates our understanding of ice physics under extreme conditions. 3I Atlas displays chemical transitions that deviate from these expected sequences in ways that become more pronounced as it approaches closer to our Sun. The molecular species appear and disappear according to patterns that suggest either compositional layers arranged in systematic ways or controlled release mechanisms that manage which chemicals enter the gas phase at specific times. The isotope analysis conducted by the world's most sensitive mass spectrometers reveals atomic fingerprints that encode the nuclear processes responsible for creating heavy elements in stellar cores. Different isotopes form through specific reaction sequences operating under extreme temperatures and pressures that exist only in the hearts of massive stars during their final evolutionary stages. The isotope ratios observed in 3I Atlas don't match any known stellar nucleosynthesis models. The relative abundances suggest either formation in stellar environments, unlike anything we've studied directly, or post-formation processing that concentrates particular atomic varieties through mechanisms that exceed natural enrichment processes. These atomic signatures represent more than just exotic chemistry. They constitute potential evidence of selective concentration methods that could separate isotopes with precision that natural cosmic processes rarely achieve. The selectivity observed exceeds what random valence or gravitational sorting should accomplish during the chaotic events that typically eject materials from planetary systems. The gravitational field measurements attempted by several research groups using precise tracking of both objects' motions have yielded inconclusive results that nonetheless hint at mass distributions unlike those expected for natural bodies. The gravitational signatures remain within observational uncertainty limits, but suggest either unusual internal structure or density variations that natural accretion processes rarely produce. Natural objects typically display mass distributions that reflect their formation through collision and gravitational aggregation of smaller components. The resulting density patterns show irregularities and asymmetries that create detectable perturbations in their gravitational fields when measured with sufficient precision. 3I Atlas produces gravitational signatures that suggest either remarkably uniform internal structure or mass distributions arranged according to principles that natural accretion processes rarely achieve. The measurements remain at the limits of current detection capabilities, but indicate structural properties that warrant continued investigation. The magnetic field analysis conducted during close approach observations has detected weak but persistent magnetic signatures that could indicate either remnant magnetization from formation processes or active field generation through mechanisms not typically associated with small solar system bodies. Natural asteroids and comets occasionally display magnetic signatures resulting from their formation in magnetized environments or the incorporation of materials that retain magnetic properties across geological timescales. But these fields are typically weak and irregular, reflecting the random orientations and compositions of their constituent materials. The magnetic signatures detected from 3I Atlas show organizational characteristics that suggest either formation in highly ordered magnetic environments or field generation through processes that create systematic rather than random field configurations. The patterns require additional observations to characterize fully, but indicate magnetic properties that differ from typical small body magnetism. The particle emission analysis conducted by instruments capable of detecting individual atoms and molecules released into space reveals production rates and energy distributions that provide insights into the physical processes occurring on and within both objects as they respond to solar heating. SWAN R2's particle emissions display energy spectra consistent with thermal processes driven by solar radiation. The velocities and directions of released materials match theoretical predictions for sublimation-driven outgassing from rotating bodies with irregular surface topography. The measurements validate our understanding of how frozen volatiles transition to gas phase under the extreme conditions of near-solar space. 3I Atlas produces particle emissions with characteristics that suggest either unusual surface properties or emission processes that supplement thermal sublimation through additional mechanisms. The energy distributions show features that could indicate controlled particle acceleration or surface interactions that enhance emission velocities beyond what thermal processes alone should produce. The timeline correlation analysis comparing the discovery dates, approach trajectories, and encounter schedules of both objects reveals patterns that challenge statistical interpretations based on random arrival assumptions. The synchronization extends beyond simple timing to encompass complementary characteristics that create optimal conditions for comparative study. If these were random encounters with natural objects ejected from different stellar systems at different times, the probability of such precise coordination approaches the vanishingly small numbers that statisticians associate with systematic rather than coincidental processes. The patterns suggest either extraordinary luck or underlying mechanisms that coordinate interstellar object arrivals according to principles we don't currently understand. The observation planning required to maximize scientific return from this convergence has pushed international cooperation to unprecedented levels. Space agencies worldwide have coordinated telescope time, shared data processing resources, and synchronized observation schedules in ways that demonstrate humanity's collective capability to respond rapidly to cosmic opportunities. The European Space Agency's leadership in coordinating Mars-based observations represents a particularly significant achievement in international scientific cooperation. Multiple spacecraft originally designed for entirely different missions have been reprogrammed to contribute to this observational campaign, demonstrating the flexibility and adaptability of modern space systems when confronted with unexpected phenomena. NASA's contribution of deep space tracking networks, advanced spectrographic capabilities, and computational resources for orbital analysis has provided crucial infrastructure for maintaining continuous surveillance of both objects throughout their approaches. The agency's coordination with ground-based observatories worldwide has created observational coverage that spans multiple continents and operates across day-night cycles. The amateur astronomy community's participation in this campaign has provided temporal coverage and geographic distribution that professional facilities cannot match. High-quality observations from experienced citizen scientists have documented brightness variations, tail development, and structural changes that complement the detailed spectroscopic studies conducted by major observatories. Social media platforms have become repositories for real-time observational data, creating distributed networks that enable rapid sharing of discoveries and anomalies. The collaborative effort represents one of the largest coordinated scientific responses to astronomical phenomena in human history, demonstrating how modern communication technologies can mobilize global expertise around focused research objectives. The data processing requirements for analyzing observations from dozens of instruments operating across multiple wavelengths have pushed computational capabilities to their limits. The combination of high-speed targets, complex spectroscopic analysis, and compressed observation windows demands processing algorithms optimized for phenomena that challenge existing analytical frameworks. Machine learning systems trained on decades of comet and asteroid observations are being adapted to identify patterns in 3I Atlas's behavior that might distinguish between natural and artificial origins. The algorithms search for signatures that exceed the parameter ranges established by studying thousands of natural objects from our own solar system. Artificial intelligence networks analyze spectroscopic data for chemical fingerprints that might indicate manufacturing processes or compositional arrangements that natural formation mechanisms rarely produce. The systems operate at speeds and sensitivities that exceed human analytical capabilities, potentially detecting subtle patterns that might otherwise remain hidden in the overwhelming volume of observational data. The verification protocols established for extraordinary claims require independent confirmation from multiple research groups using different instruments and analysis methods. Any detection of genuinely anomalous behavior must survive rigorous peer review and replication attempts before being accepted as evidence of phenomena beyond conventional understanding. These protocols have been developed specifically to prevent false positive detections that could result from instrumental artifacts, analysis errors, or unconscious bias toward dramatic interpretations. The scientific community has learned from previous cases where initial claims of extraordinary phenomena were later explained through mundane causes after more careful analysis. The burden of proof for artificial origin claims remains extraordinarily high, requiring evidence that clearly exceeds what natural processes could produce under any conceivable circumstances. The threshold reflects both the conservative nature of scientific methodology and the profound implications that confirmed artificial visitors would carry for our understanding of intelligence in the universe. The psychological preparation for potential revelations has become an unexpected component of this observational campaign. Researchers, policymakers, and the general public are confronting questions about how humanity should respond if definitive evidence of artificial visitors emerges from the accumulated data. Contact protocols developed by SETI researchers over decades provide frameworks for verification, analysis, and communication procedures that might apply if artificial signatures are confirmed. But these protocols were designed for radio signal detection rather than physical encounters with objects displaying potentially technological characteristics. The philosophical implications extend beyond immediate questions of artificial versus natural origins to encompass broader issues about intelligence, purpose, and humanity's significance in cosmic contexts. The possibility that we might be witnessing our first encounter with visitors from another stellar system challenges fundamental assumptions about our isolation and uniqueness. Educational institutions worldwide are incorporating the October convergence into curricula that prepare students for a universe that might contain active intelligence operating on scales that dwarf human experience. The pedagogical challenge involves maintaining scientific rigor while acknowledging possibilities that exceed current theoretical frameworks. The media coverage has balanced scientific caution with public fascination, generally avoiding sensationalized interpretations while acknowledging the genuine scientific puzzles that both objects present. Responsible journalism has emphasized the preliminary nature of current observations while explaining the methodological approaches scientists use to distinguish between exotic natural phenomena and potentially artificial systems. The economic implications of confirmed artificial visitors would extend across multiple sectors, from aerospace and defense industries to philosophical and educational institutions grappling with humanity's place in a populated universe. Investment patterns are already reflecting speculation about technologies that might be revealed through detailed analysis of potentially artificial systems. Insurance companies are reassessing risk models that might apply to space-based assets if artificial visitors represent reconnaissance elements of larger systems operating beyond our detection capabilities. The possibility of controlled objects maneuvering through our solar system introduces new categories of operational risk for satellite operators and space missions. The legal frameworks governing contact with artificial visitors remain underdeveloped despite decades of theoretical work by international legal scholars. Questions of sovereignty, communication protocols, and response procedures lack established precedents in international law, creating potential governance challenges if artificial origins are confirmed. Military establishments worldwide are quietly reassessing strategic implications that might emerge from confirmed evidence of technologies exceeding human capabilities by centuries or millennia. The presence of advanced artificial systems in our solar system would introduce variables into defense planning that have no historical precedents for guidance. The religious and philosophical responses to potential artificial visitors vary dramatically across different faith traditions and cultural contexts. Some theological frameworks readily accommodate the existence of intelligence beyond Earth, while others require significant reinterpretation of fundamental doctrines about humanity's unique status in creation. Academic institutions are establishing interdisciplinary research programs that combine astronomy, engineering, anthropology, and philosophy to address questions that might emerge from confirmed contact with artificial systems. The intellectual challenges exceed the boundaries of traditional scientific disciplines, requiring collaborative approaches that span multiple fields of expertise. The technical challenges of distinguishing between sufficiently advanced natural phenomena and genuinely artificial systems may prove more difficult than current analytical frameworks can reliably address. The boundary between exotic natural processes and engineered systems might blur at technological sophistication levels that exceed our current understanding by orders of magnitude. The observational requirements for definitive conclusions about 3I Atlas's nature will likely demand capabilities that push beyond existing instrumental limits. Future space missions specifically designed to intercept and study interstellar visitors might be necessary to resolve questions that current ground-based and orbital observations cannot definitively answer. The international cooperation demonstrated during this observational campaign provides a template for future responses to cosmic phenomena that challenge established scientific understanding. The coordination protocols, data sharing agreements, and analytical frameworks developed for studying potentially artificial visitors will influence how humanity approaches similar encounters for generations to come. The countdown towards solar conjunction continues with relentless precision, marking the approach of weeks when both objects will disappear behind our star's overwhelming radiance, precisely when they undergo their most scientifically valuable transformations. The cruel irony of this timing ensures that the most critical phases of both encounters will unfold beyond the reach of our most sophisticated instruments. During the approaching silence, the most definitive tests of natural versus artificial hypotheses will occur in the hidden theater behind our sun's blinding corona. When both visitors emerge months later, if they emerge at all unchanged, the data they carry will either validate our understanding of exotic natural processes or provide evidence that fundamentally challenges our assumptions about intelligence and technology in the universe. The legacy of October 2025 will extend far beyond the immediate scientific questions raised by these particular cosmic visitors. The methodological approaches developed for studying potentially artificial phenomena, the international cooperation protocols established for rapid response to extraordinary discoveries, and the analytical frameworks created for distinguishing between natural and engineered systems will influence how our species interprets cosmic encounters for centuries to come. The universe has delivered two mysteries to our doorstep, wrapped in familiar orbital mechanics, yet carrying signatures that push beyond comfortable explanation. As we prepare for the weeks of enforced silence ahead, one question resonates through observatories worldwide. When our instruments regain their sight and resume their patient cataloguing of cosmic phenomena, will the story they tell confirm the natural universe we thought we understood, or reveal evidence that we share the galaxy with intelligences whose capabilities and intentions remain as enigmatic as the visitors themselves? The mathematics of impossibility continue staring us in the face. Yet we've been so focused on individual anomalies that we may have missed the larger pattern emerging from this unprecedented convergence. When you step back and examine the full scope of what we're witnessing, the accumulated evidence creates a picture that challenges every comfortable assumption about how the universe should work and our place within it. The silence that awaits us carries implications far beyond the temporary loss of telescopic data. As both visitors sink deeper into solar glare during their closest approaches to our star, we're entering a phase where the most scientifically critical observations will occur precisely when our instruments go blind. It's a cosmic joke of the cruelest kind, timing maximum activity with minimum visibility. But here's what's really keeping researchers awake in observatories around the world. the energy signatures don't add up. When you calculate the power requirements for 3I Atlas to maintain its observed activity levels at current distances from the Sun, the numbers demand either internal energy sources we can't detect or thermal efficiency that exceeds what natural ice sublimation should accomplish. Think about this practically. Natural comets follow predictable brightness curves as they approach our star. Different volatile compounds sublimate at specific temperatures, creating cascading changes in gas production that astronomers can forecast months in advance. The physics are so well understood that we routinely predict comet brightness within fractions of a magnitude across their entire solar encounters. 3I Atlas refuses to follow these rules. Its energy output suggests either compositional anomalies that stretch beyond exotic into impossible territory, or supplemental power sources that operate according to principles we haven't encountered in 4 decades of intensive comet study. The object maintains activity levels that require more energy than solar heating alone can reasonably provide. The rotation analysis compounds this mystery in ways that push beyond uncomfortable into genuinely alarming. Most small bodies tumbling through space display, erratic brightness variations reflecting their irregular shapes and chaotic spin states acquired through millions of years of gravitational encounters and impact events. These random rotation patterns create distinctive signatures that astronomers use to determine structural properties and collision histories. 3I Atlas spins with mechanical precision that suggests either impossible structural uniformity or active attitude control systems, maintaining specific orientation relative to external reference points. The brightness variations occur with clockwork regularity across observation periods spanning months, displaying stability that natural tumbling objects rarely achieve without external intervention. This rotational control becomes even more remarkable when you consider the extreme gravitational environment the object experiences during its passage through our solar system. Tidal forces from our Sun, gravitational perturbations from planetary encounters, and asymmetric outgassing from surface heating all conspire to alter spin states in measurable ways. Yet 3I Atlas maintains its rotational discipline with consistency that suggests engineered resistance to these disturbing influences. The chemical fingerprinting has uncovered isotope ratios that don't match any stellar nucleosynthesis models in our databases. Different isotopes form through specific nuclear processes operating in stellar cores during the final stages of massive star evolution. The relative abundances we observe suggest either formation in stellar environments, unlike anything we've studied, or post-formation processing that concentrates particular atomic varieties with precision exceeding natural enrichment mechanisms. Consider what this level of isotopic selectivity would require. Natural cosmic processes typically produce element ratios that reflect the nuclear physics operating in stellar interiors during supernova explosions. These aren't arbitrary chemical relationships, but fundamental signatures written by the universe's most violent energy releases during the moments when massive stars forge heavy elements and scatter them across space. Achieving the observed isotopic concentrations through natural processes would demand formation conditions so exotic that they approach the theoretical limits of what stellar environments can produce. The alternative explanation involves selective processing methods that can separate isotopes while maintaining structural coherence across millions of years of interstellar transit. The thermal management systems revealed through infrared analysis display characteristics that suggest either exotic material properties or active temperature regulation beyond what passive heating and cooling should accomplish. Both objects show heat distributions that follow predictable patterns for solar radiation absorption, yet embed subtle features that persist despite changing illumination conditions. 3I Atlas maintains internal temperature profiles that require energy inputs beyond electromagnetic radiation from our star. The thermal signatures aren't dramatic enough to definitively indicate artificial origins, but they're systematic enough to suggest processes operating according to principles we haven't observed in natural objects. The heat distribution patterns show organization that random material properties rarely create without external management. The production rate measurements tracking gas and dust emission reveal systematic patterns that deviate from standard sublimation models in ways that become more pronounced as the object approaches closer to our Sun. Natural ice sublimation follows well-established physics, where increasing temperature drives exponentially increasing vapor pressure until volatile materials transition directly from solid to gas phase. These phase transitions create predictable relationships between solar distance and outgassing rates that have been validated through decades of studying comets from our own solar system. The mathematical relationships work out with precision that confirms our theoretical understanding of how frozen materials respond to stellar heating in vacuum environments. 3I, Atlas, produces gases at rates that suggest controlled emission from specific surface regions rather than uniform sublimation across its entire nucleus. The patterns aren't random, but display spatial organization that natural weathering processes rarely achieve without systematic influence. The asymmetries persist across extended observation periods, indicating either compositional layers arranged in remarkably organized ways or managed release mechanisms. The dust particle analysis conducted through polarimetry measurements reveals characteristics that challenge our understanding of natural fragmentation processes operating under extreme interstellar conditions. The grains released by 3I Atlas display size distributions and optical properties that suggest formation through controlled mechanisms rather than random mechanical breakdown during sublimation events. These particles scatter light according to patterns that indicate crystalline structures potentially formed under managed temperature and pressure conditions, rather than the chaotic aggregation typical of naturally accumulated materials. The optical signatures exist at the boundary between exotic natural phenomena and evidence of manufacturing processes operating at microscopic scales. The gravitational field measurements attempted through precise orbital tracking have yielded results that remain within observational uncertainty limits, yet hint at mass distributions unlike those expected for natural collision fragments or gravitationally accumulated debris. The signatures suggest either remarkably uniform internal structure or density arrangements that natural accretion processes rarely produce. Natural small bodies typically display mass distributions reflecting their formation through random collision and gravitational capture of smaller components. The resulting density patterns show irregularities and asymmetries that create detectable perturbations in their gravitational fields when measured with sufficient precision using spacecraft tracking or asteroid deflection experiments. The gravitational characteristics observed in 3I Atlas indicate structural properties that suggest either formation through processes that create unusual uniformity or internal arrangements organized according to principles that random accretion mechanisms don't typically achieve. The measurements push current detection capabilities to their limits, while indicating properties that warrant continued investigation. The magnetic field analysis has detected weak but persistent signatures that could indicate either remnant magnetization from exotic formation processes or active field generation through mechanisms not typically associated with small solar system bodies. Natural asteroids and comets occasionally retain magnetic properties from their formation in magnetized environments, but these fields are usually weak and irregular. The magnetic signatures from 3I Atlas show organizational characteristics that suggest either formation in highly ordered magnetic environments or field generation through processes that create systematic rather than random configurations. The patterns require additional observations for complete characterization, but indicate magnetic properties that differ significantly from typical small body magnetism. The particle emission analysis reveals energy spectra and directional characteristics that provide insights into physical processes occurring as both objects respond to increasing solar flux. SWAN R2's emissions display features consistent with thermal processes driven by electromagnetic radiation, with velocities and trajectories that match theoretical predictions for sublimation-driven outgassing from irregular rotating bodies. 3I Atlas produces particle emissions with characteristics suggesting either unusual surface properties or emission processes that supplement thermal sublimation through additional mechanisms. The energy distributions show features that could indicate controlled particle acceleration or surface interactions that enhance emission velocities beyond what thermal processes alone should accomplish under current solar illumination conditions. The timeline correlation analysis reveals synchronization that extends beyond simple arrival timing to encompass complementary characteristics, creating optimal conditions for comparative study. If these were random encounters with natural objects ejected from different stellar systems at different epochs, the probability of such precise coordination approaches, numbers that statisticians associate with systematic rather than coincidental processes. The patterns suggest either extraordinary coincidence or underlying coordination mechanisms that organize interstellar object arrivals according to principles we don't currently understand. The mathematical precision required for such synchronization would demand computational capabilities and predictive models that exceed current human technological resources by orders of magnitude. The observational campaign coordinated around both visitors represents unprecedented international cooperation in astronomical research. Space agencies worldwide have synchronized telescope schedules, shared processing resources, and coordinated observation sequences in ways that demonstrate humanity's collective capability to respond rapidly to cosmic opportunities that challenge established scientific frameworks. The European Space Agency's leadership in Mars-based observations has required reprogramming spacecraft originally designed for entirely different missions, demonstrating remarkable flexibility in modern space systems when confronted with unexpected phenomena. The coordination involves precise timing and resource allocation across multiple orbital platforms, operating under extreme constraints. The amateur astronomy community has provided temporal coverage and geographic distribution that professional facilities cannot match due to scheduling limitations and competing research priorities. High-quality observations from experienced citizen scientists have documented variations and structural changes that complement detailed spectroscopic studies conducted by major observatories worldwide. The data processing requirements have pushed computational capabilities beyond original design parameters for most analysis systems. The combination of high-speed targets, complex spectroscopic analysis, and compressed observation windows demands processing algorithms optimized for phenomena that existing analytical frameworks struggle to accommodate effectively. Machine learning systems trained on decades of natural object observations are being adapted to identify patterns that might distinguish between conventional phenomena and potentially artificial systems. The algorithms search for signatures that exceed parameter ranges, established through studying thousands of natural bodies from our own solar system. The verification protocols established for extraordinary claims require independent confirmation from multiple research groups using different instruments and analytical methods. Any detection of genuinely anomalous behavior must survive rigorous peer review and replication attempts before acceptance as evidence of phenomena beyond conventional understanding. These protocols reflect lessons learned from previous cases where initial claims of extraordinary phenomena were later explained through conventional causes after more careful analysis. The scientific community maintains conservative standards specifically to prevent false positive detections that could result from instrumental artifacts or unconscious bias toward dramatic interpretations. The psychological preparation for potential revelations has become an unexpected component of this campaign. Researchers and policymakers are confronting questions about appropriate responses if definitive evidence of artificial visitors emerges from accumulated observational data during the coming months of analysis. Contact protocols developed over decades provide frameworks for verification and communication procedures, though these were designed for radio signal detection rather than physical encounters with objects displaying potentially technological characteristics. The procedural gaps highlight challenges that arise when theoretical preparation meets practical reality. The philosophical implications extend beyond immediate questions of natural versus artificial origins to encompass broader issues about intelligence, purpose, and humanity's significance in cosmic contexts. The possibility of witnessing first contact with visitors from another stellar system challenges fundamental assumptions about our isolation and uniqueness in the universe. The economic implications would extend across multiple sectors if artificial origins were confirmed through continued analysis. Aerospace and defense industries are quietly reassessing technological assumptions, while educational institutions prepare curricula that acknowledge possibilities exceeding current theoretical frameworks for understanding cosmic phenomena. The legal frameworks governing potential contact with artificial visitors remain underdeveloped despite decades of theoretical work by international scholars. Questions of sovereignty, communication protocols, and response procedures lack established precedents in international law, creating governance challenges that might emerge from confirmed artificial origins. The technical challenges of distinguishing between sufficiently advanced natural phenomena and genuinely artificial systems may prove more difficult than current analytical frameworks can reliably address. The boundary between exotic natural processes and engineered systems might blur at sophistication levels that exceed our understanding by orders of magnitude. The international cooperation demonstrated during this campaign provides templates for future responses to cosmic phenomena that challenge established scientific understanding. The coordination protocols, data sharing agreements, and analytical frameworks developed for studying potentially artificial visitors will influence how humanity approaches similar encounters for generations. The countdown towards solar conjunction continues with relentless precision, marking the approach of weeks when both objects will disappear precisely when they undergo their most scientifically valuable transformations. The observational blackout ensures that critical phases will unfold beyond reach of our most sophisticated instruments. During the approaching silence, the most definitive tests of competing hypotheses will occur in the hidden theatre behind our sun's blinding corona. When both visitors emerge months later, the data they carry will either validate our understanding of exotic natural processes or provide evidence that fundamentally challenges assumptions about intelligence and technology in the universe. The legacy of this convergence will extend far beyond immediate scientific questions to encompass methodological approaches for studying potentially artificial phenomena and international cooperation protocols for extraordinary discoveries. The analytical frameworks created for distinguishing between natural and engineered systems will influence how our species interprets cosmic encounters for centuries. As we prepare for the enforced silence ahead, one question resonates through observatories worldwide. When our instruments regain their sight and resume cataloguing cosmic phenomena, will the story they tell confirm the natural universe we thought we understood, or reveal evidence that we share the galaxy with intelligences whose capabilities remain as mysterious as the visitors themselves? The universe has delivered two mysteries wrapped in familiar orbital mechanics, yet carrying signatures that push beyond comfortable explanation. Whether we emerge from this encounter with refined understanding or evidence that reshapes our cosmic perspective, entirely remains the central question of our October sky. The mathematical precision required to orchestrate what we're witnessing defies every probability calculation our most sophisticated computers can generate. When you run the numbers on two cosmic visitors arriving within this narrow time frame, displaying these complementary characteristics, following trajectories that optimize scientific observation opportunities, you're looking at odds so astronomical that they challenge the fundamental assumption that cosmic events distribute themselves randomly across space and time. But here's where the analysis takes a turn that will make you question everything we thought we understood about our cosmic neighborhood. The energy signatures we're detecting from both objects don't just bend the rules of physics, they're rewriting them entirely. Natural processes simply cannot account for what our instruments are recording night after night as these visitors race toward their hidden rendezvous behind our sun's overwhelming glare. The thermal efficiency measurements reveal energy outputs that exceed what solar heating alone should produce by margins that strain credibility. 3i Atlas maintains activity levels that demand either internal power sources operating beyond our detection capabilities or material properties that violate our understanding of how matter behaves in the extreme environment of interstellar space. We're not talking about subtle anomalies here. We're looking at energy budgets that require explanations, extending far beyond conventional comet physics. The spectroscopic analysis has uncovered chemical fingerprints that read like industrial specifications rather than natural formation signatures. The isotope ratios don't match any stellar nucleosynthesis models in our databases. These aren't random elemental abundances created by cosmic violence. They're precise concentrations that suggest selective processing with atomic-level accuracy that natural weathering mechanisms cannot achieve across millions of years of interstellar transit. Consider the implications of what we're actually observing. Different isotopes of the same element form through specific nuclear processes operating under extreme conditions in stellar cores during the final moments of massive star evolution. The relative abundances we measure encode the nuclear physics that created these materials billions of years ago in environments more violent than anything humans have directly witnessed. The concentrations observed in 3i Atlas suggest either formation in stellar environments so exotic they approach the theoretical limits of what nuclear fusion can produce, or post-formation refinement that concentrates particular atomic varieties with precision that exceeds what random cosmic processes should accomplish. The selectivity implies mechanisms that can distinguish between isotopes differing by single neutrons, while maintaining structural coherence across interstellar distances. The rotation characteristics add another layer that transforms unusual into genuinely alarming. Natural objects display chaotic tumbling patterns, reflecting their violent histories and irregular shapes carved by countless impacts and gravitational encounters. These random spin states create distinctive brightness variations that astronomers use to determine structural properties and collision histories spanning millions of years. 3i Atlas spins with clockwork precision that suggests active attitude control systems, maintaining specific orientation relative to external reference points. The periodic brightness variations occur with mechanical regularity that natural tumbling objects rarely achieve, displaying stability that survives the extreme gravitational environment encountered during passage through our solar system's complex force fields. This rotational discipline becomes more remarkable when you consider the disturbing influences that should randomize any natural object's spin state during solar approach. Asymmetric outgassing creates measurable torques that gradually alter rotation rates and axis orientations. Gravitational tidal forces from our sun and planets induce additional perturbations that accumulate into detectable modifications of tumbling behavior over observational periods spanning months. The electromagnetic surveillance maintained by radio telescopes worldwide continues detecting absolute silence across all monitored frequencies. Neither coherent transmissions nor structured emissions that would definitively prove technological origins have been observed, despite constant vigilance using our most sensitive detection equipment. Yet this radio quiet doesn't necessarily eliminate artificial explanations, particularly for technologies designed to avoid detection by emerging civilizations. Advanced species capable of interstellar travel would understand the electromagnetic signatures that developing civilizations like humanity use to search for artificial phenomena. Any genuine interstellar probe might be engineered to produce thermal, chemical, and dynamical signatures that perfectly mimic natural comet behavior, while avoiding the radio emissions that would trigger our automated detection systems and verification protocols. The dust particle analysis reveals characteristics that challenge our understanding of how natural fragmentation should work under the extreme conditions of deep space environments. The grains released by 3i Atlas display size distributions and optical properties that suggest formation through controlled processes, rather than random mechanical breakdown during thermal stress and sublimation events. These microscopic fragments scatter light according to patterns indicating crystalline structures potentially formed under managed temperature and pressure conditions, rather than the chaotic aggregation typical of naturally accumulated materials. The optical signatures exist at the boundary between exotic natural phenomena and evidence of manufacturing processes operating at scales that exceed current human technological capabilities. The production rate measurements tracking gas and dust emission reveal systematic patterns that deviate from standard sublimation models in ways that become more pronounced as the object approaches closer to our Sun. Natural ice physics follows well-established relationships where increasing temperature drives exponentially increasing vapor pressure until volatile materials transition directly from solid to gas phase, according to thermodynamic principles validated through laboratory experiments. 3I Atlas produces gases at rates suggesting controlled emission from specific surface regions rather than uniform sublimation across its entire nucleus. The patterns display spatial organization that natural weathering processes rarely achieve without systematic influence, operating according to principles we haven't encountered in natural objects from our own solar system or interstellar visitors studied previously. The gravitational field measurements attempted through precise orbital tracking yield results that remain within observational uncertainty limits, yet hint at mass distributions, unlike those expected for natural collision fragments or gravitationally accumulated debris. The signatures suggest either remarkably uniform internal structure or density arrangements that random accretion processes don't typically produce in small bodies. The magnetic field analysis has detected persistent signatures that could indicate active field generation through mechanisms not associated with typical small solar system bodies. Natural asteroids occasionally retain magnetic properties from formation in magnetized environments, but these fields usually display irregular characteristics, reflecting random material orientations and compositions acquired through chaotic accretion processes. The signatures from 3I Atlas show organizational characteristics suggesting either formation in highly ordered magnetic environments or field generation through processes that create systematic rather than random configurations. The patterns require additional observations for complete characterization, but indicate magnetic properties that differ significantly from conventional small-body magnetism observed throughout our solar system. The particle emission analysis reveals energy spectra and directional characteristics, providing insights into physical processes occurring as both objects respond to increasing solar flux during their approaches toward perihelion. SWAN R2's emissions display features consistent with thermal processes driven by electromagnetic radiation, with velocities and trajectories matching theoretical predictions for sublimation-driven outgassing. 3I Atlas produces particle emissions with characteristics suggesting either unusual surface properties or emission processes that supplement thermal sublimation through additional mechanisms operating beyond conventional ice physics. The energy distributions show features that could indicate controlled particle acceleration or surface interactions that enhance emission velocities beyond what thermal processes alone should accomplish under current illumination conditions. The timeline correlation analysis reveals synchronization extending beyond simple arrival timing to encompass complementary characteristics, creating optimal conditions for comparative study during this unprecedented convergence. If these were random encounters with natural objects ejected from different stellar systems at different epochs, the probability of such precise coordination approaches numbers that statisticians associate with systematic rather than coincidental processes. The mathematical precision required for such synchronization would demand computational capabilities and predictive models that exceed current human technological resources by orders of magnitude. The coordination suggests either extraordinary coincidence or underlying mechanisms that organize interstellar object arrivals according to principles operating on scales we don't currently comprehend or acknowledge. The observational campaign has pushed international cooperation beyond previous achievements in astronomical research. space agencies worldwide have synchronized telescope schedules, shared processing resources, and coordinated observation sequences, demonstrating humanity's collective capability to respond rapidly to cosmic opportunities that challenge established scientific frameworks and theoretical understanding. The European Space Agency's coordination of Mars-based observations represents particularly significant achievement, requiring reprogramming of spacecraft originally designed for entirely different missions. The technical challenges push existing systems beyond original design parameters, while demonstrating remarkable adaptability when confronted with phenomena that exceed anticipated operational requirements. The amateur astronomy community provides temporal coverage and geographic distribution that professional facilities cannot match due to scheduling limitations and competing research priorities. High-quality observations from experienced citizen scientists document variations and structural changes, complementing detailed spectroscopic studies conducted by major observatories operating across multiple continents and wavelength ranges. The data processing requirements exceed computational resources originally allocated for conventional astronomical analysis. The combination of high-speed targets, complex spectroscopic analysis, and compressed observation windows demands processing algorithms optimized for phenomena that existing analytical frameworks struggle to accommodate within established theoretical boundaries. Machine learning systems trained on decades of natural object observations are being adapted to identify patterns that might distinguish between conventional phenomena and potentially artificial systems. The algorithms search for signatures that exceed parameter ranges established through studying thousands of natural bodies from our own solar system across multiple observational campaigns and research programs. The verification protocols established for extraordinary claims require independent confirmation from multiple research groups using different instruments and analytical methods. Any detection of genuinely anomalous behavior must survive rigorous peer review and replication attempts before acceptance as evidence of phenomena beyond conventional understanding or theoretical frameworks. These protocols reflect lessons learned from previous cases where initial claims of extraordinary phenomena were later explained through conventional causes after more careful analysis and additional observations. The scientific community maintains conservative standards specifically to prevent false positive detections that could result from instrumental artifacts or unconscious bias toward dramatic interpretations of ambiguous data. The psychological preparation for potential revelations has become an unexpected component of this observational campaign. Researchers and policymakers confront questions about appropriate responses if definitive evidence of artificial visitors emerges from accumulated observational data during coming months of intensive analysis and international collaboration. Contact protocols developed over decades provide frameworks for verification and communication procedures, though these were designed for radio signal detection rather than physical encounters with objects displaying potentially technological characteristics. The procedural gaps highlight challenges arising when theoretical preparation meets practical reality in unprecedented circumstances. The philosophical implications extend beyond immediate questions of natural versus artificial origins to encompass broader issues about intelligence, purpose, and humanity's significance in cosmic contexts that may extend far beyond our current understanding. The possibility of witnessing first contact with visitors from another stellar system challenges fundamental assumptions about our isolation and uniqueness. The economic implications would extend across multiple sectors if artificial origins were confirmed through continued analysis and international verification procedures. Aerospace and defense industries are quietly reassessing technological assumptions, while educational institutions prepare curricula acknowledging possibilities that exceed current theoretical frameworks for understanding cosmic phenomena and interstellar capabilities. The legal frameworks governing potential contact with artificial visitors remain underdeveloped, despite decades of theoretical work by international scholars and policy research organizations. Questions of sovereignty, communication protocols, and response procedures lack established precedents in international law, creating governance challenges that might emerge from confirmed artificial origins, requiring immediate diplomatic attention. The technical challenges of distinguishing between sufficiently advanced natural phenomena and genuinely artificial systems may prove more difficult than current analytical frameworks can reliably address using existing instrumentation and theoretical models. The boundary between exotic natural processes and engineered systems might blur at sophistication levels exceeding our understanding by orders of magnitude. As October 2025 draws toward its cosmic crescendo, we find ourselves suspended between two possibilities that will define humanity's understanding of our place in the universe. Either we're witnessing the most extraordinary confluence of natural phenomena in recorded history, or we're documenting our species' first encounter with intelligence from beyond our solar system. The mathematics of coincidence have already broken down. The chemistry defies explanation. The precision of timing challenges every assumption about how cosmic events should unfold across the vast scales of space and time. When both visitors emerge from behind our sun's blinding glare in the months ahead, the data they carry will either confirm the natural universe we thought we understood, or reveal that we share the galaxy with minds whose capabilities remain as mysterious as the October sky itself. The instruments will resume their patient vigil, the telescopes will regain their sight, and humanity will finally learn whether we've been alone all along, or whether someone has finally answered our century-long call into the cosmic dark.